Hello there and welcome to Physics with William, a quiet place where big ideas are allowed to slow down a little, where curiosity doesn't have to rush, and where science can unfold at a pace that's meant for listening rather than skimming. Tonight, we're going to spend some time with something so familiar that it's almost invisible, something you rely on constantly without ever really watching it work. It's there when you wake up, when you make tea, when you check the time, when you turn out the lights, and when you finally settle back into the dark. And yet, despite how deeply it's woven into modern life, it remains strangely elusive. We're talking about electricity, not as a list of equations or technical diagrams, but as a quiet force that hums through everything we do. Electricity has a curious way of being both dramatic and mundane at the same time. On one hand, it can tear across the sky in a flash of lightning, loud enough to rattle windows and remind us how small we are. On the other, it sits patiently behind a plastic switch, waiting to be invited into action with the smallest movement of a finger. It can be dangerous, life-saving, invisible, and utterly essential, sometimes all at once. And yet most days we don't think about it at all. We expect it. We assume it will be there. When it isn't, we're reminded very quickly of just how much of the modern world depends on something we never actually see. So before we go any further, take a moment to notice where you are right now. Are you listening late at night, with the lights low and the rest of the world quiet? Or is this part of a daytime routine, playing softly in the background while something else hums nearby? Where are you listening from, and what's happening around you at this exact moment? Somewhere close by, electricity is moving. Through wires in the walls, through circuits in your phone or computer, through lights, chargers, routers, screens. It's already part of this moment, whether you're paying attention to it or not. If you find this kind of slow, careful exploration soothing or interesting, if it helps you unwind or simply gives your mind something gentle to rest on, then liking the video or subscribing is always appreciated. It helps this calm little corner find others who might need it too. But for now, there's nothing you need to do. Just listen. There's no test at the end. No rush to understand everything all at once. We'll take our time. Because electricity, despite how technical it can sound, is ultimately a story about motion. About tiny things moving in organized ways. About humans learning how to notice, guide, and eventually depend on that motion. It's not a story that starts with power plants or outlets or glowing screens. It starts much earlier, long before anyone knew what a volt or an ampere was. It starts with observation, with curiosity, with the simple realization that the world sometimes behaves in ways that aren't obvious at first glance. Think about how strange it is that you can press a button and a room instantly fills with light, or that you can speak into a small object in your hand and be heard on the other side of the planet, or that food can be kept cold for days, messages can travel faster than sound, and entire cities can remain awake long after the sun has gone down. None of that happens because electricity is intelligent or intentional. It happens because humans learned how to work with a natural phenomenon that was always there, waiting to be noticed. For most of human history, electricity was not something people used. It was something they occasionally encountered. A shock from touching a certain fish. A spark when materials were rubbed together. A sudden bolt of lightning with no warning and no clear cause. These moments were surprising, sometimes frightening, and often wrapped in myth. Electricity wasn't understood as a system. It was experienced as an event. Something that happened to you, not something you controlled. Even now, when electricity is so carefully managed that it rarely surprises us, it still carries that sense of mystery. You can know, intellectually, that flipping a switch completes a circuit and allows electrons to move, but that doesn't change how strange it feels that the room responds instantly. The cause and effect are so closely linked that the process in between disappears. Electricity does its work quietly, without announcing itself, and that makes it easy to forget how much is actually happening behind the scenes. At its core, electricity is about charged particles and how they behave. But that simple statement hides an enormous amount of detail. It hides the structure of atoms, the balance of forces, and the conditions that allow energy to move from one place to another. It hides the fact that nothing in your home is powered by electricity in isolation. Every device, every light, every screen is part of a much larger network, stretching outward through neighborhoods, cities, and landscapes, back to places where energy is being generated, converted, and sent on its way. When people talk about electricity, they often talk about it as if it were a substance, like water flowing through pipes. That comparison is sometimes useful, but it can also be misleading. Electricity isn't a thing that gets used up in the same way water does. It's more like a process, a coordinated movement that only works when everything is connected properly. When something breaks in that chain, the movement stops, and suddenly nothing works the way it should. That's one of the reasons electricity feels so all or nothing. When it's there, life continues smoothly. When it's gone, everything changes at once. Lights go dark, screens go blank, sounds stop mid-sentence. And in that sudden silence, we're reminded that electricity isn't just a convenience. It's infrastructure. It's a foundation that modern life quietly rests on. But electricity isn't only something that powers machines. It's also something that exists inside living things. Your nervous system relies on electrical signals to move information. Your muscles contract because of changes in electrical charge. Even your heart keeps its rhythm through carefully timed electrical impulses. Long before humans built generators or batteries, electricity was already part of biology, guiding movement, sensation, and response. That raises an interesting question. If electricity has always been part of the natural world, why did it take so long for humans to learn how to use it deliberately? The answer has less to do with intelligence and more to do with scale. The electrical effects that happen naturally in living organisms are incredibly small. They're precise, localized, and difficult to detect without specialized tools. For most of history, humans simply didn't have the means to notice them in a systematic way. What they did notice were the bigger, more obvious effects: static sparks, lightning, certain materials attracting or repelling one another after being rubbed. These weren't immediately recognized as related phenomena. They were isolated curiosities, interesting but disconnected. It took centuries of observation, experimentation, and gradual refinement before anyone began to suspect that these effects might all be part of the same underlying behavior. Even then, progress was slow. Not because people weren't curious, but because electricity doesn't behave in ways that are easy to see directly. You can watch a fire burn. You can feel wind push against you. You can see water flow downhill. Electricity, by contrast, does its work inside materials, along paths that are hidden from view. To understand it, you have to infer its presence from what it does, not from what it looks like. That challenge shaped the way electricity was studied. Early experiments were simple, sometimes almost playful. Rubbing materials together, storing charge, watching sparks jump between objects. Over time, those experiments became more controlled, more precise, and more ambitious. Each step revealed a little more about how electric charge behaves, how it can be guided, and how it interacts with matter. What's remarkable is that once those patterns began to emerge, everything else followed quickly. Once humans learned how to create a steady flow of electrical charge, rather than brief, unpredictable sparks, electricity transformed from a curiosity into a tool. From there, it became a technology, and eventually it became a necessity. Still, even as electricity reshaped the world, the basic experience of it didn't change much. You still don't see it directly. You see its effects: light, motion, heat, sound, information. Electricity itself remains hidden, moving silently through metal and silicon, obeying rules that are strict but not intuitive. That hidden quality is part of what makes electricity such a compelling subject. It sits at the intersection of the visible and the invisible, the natural and the engineered. It's governed by physical laws that are well understood, and yet it still feels slightly magical in everyday life. You don't need to understand it to depend on it, and most of the time, you don't need to think about it at all. But thinking about it can change the way the world feels. It can turn ordinary objects into quiet demonstrations of physics at work. A lamp becomes a carefully balanced system. A charger becomes a controlled exchange of energy. A power line becomes part of a vast coordinated effort to keep electrons moving in just the right way, at just the right time. As we move forward, we'll stay grounded in that perspective. Not electricity as a collection of formulas, but electricity as a process that connects atoms, machines, and living systems. We'll look at where it comes from, how it moves, how it's stored, and how it's controlled. We'll talk about the choices humans made along the way, the mistakes, the debates, and the designs that shape the electrical world you live in now. And none of this exists in isolation. Electricity doesn't suddenly appear at the wall socket fully formed. It arrives there after a long journey, shaped by chemistry, physics, engineering, and history. To understand what makes everything work, you have to trace that journey backward, step by step, from the familiar to the fundamental. So as you listen, there's no need to hold on to every detail. Let the ideas settle naturally. Some will feel obvious, others might feel surprising. All of them are connected by the same underlying theme, motion guided by structure. That's the quiet principle behind electricity, and it's what allows an invisible process to become the backbone of the modern world. With that in mind, it makes sense to begin not with power stations or grids, but with the simple question of presence. How electricity became so woven into daily life that its absence feels more noticeable than its operation. Because before we can understand how electricity works, it helps to notice just how often it's already at work around us, shaping routines, habits, and expectations in ways that are easy to overlook when everything's running smoothly. Electricity is so deeply embedded in everyday life that it often disappears into the background, not because it is subtle, but because it is reliable. The more consistently something works, the less attention it attracts. A light turns on when a switch is flipped. A screen wakes up when a button is pressed. A familiar hum fills the room when a refrigerator cycles on. None of these moments feel remarkable, yet each one depends on a precise and continuous movement of electrical charge. The quietness of electricity is not a sign of simplicity. It is a sign of careful design layered over something inherently restless. From the moment you wake up, electricity is already shaping your environment. An alarm sounds at a chosen time, not because time itself makes noise, but because an electronic circuit has been counting oscillations with steady accuracy. The room may be dim or bright depending on artificial light rather than the sun. The temperature is likely regulated by a system that measures electrical signals from sensors and responds automatically. Even before you actively interact with anything, electricity is maintaining conditions that feel normal enough to ignore. What makes this presence so easy to miss is that electricity rarely announces itself. It does not need attention to function. It moves through wires, components, and devices with a consistency that masks its complexity. Unlike mechanical systems, which often reveal their operation through movement and sound, electrical systems can operate silently. There are no visible gears turning when data is transferred, no obvious motion when information is processed. The work is happening, but it is happening at scales and speeds that human senses are not equipped to detect directly. Consider how many objects around you depend on electricity even when they are not actively in use. A television that appears off is still often drawing a small amount of power. A router quietly maintains a connection, ready to send and receive information at any moment. Chargers left plugged into outlets continue to interact with the electrical system whether or not a device is attached. Electricity is not only something that responds when called upon, it is something that maintains readiness, holding systems in a state of potential. This constant availability shapes expectations in subtle ways. When electricity is always present, it becomes a baseline assumption rather than a feature. The idea that light might not be available after sunset feels unusual in many parts of the world. The idea that communication might take days instead of seconds feels distant, almost historical. Electricity has compressed time and space in ways that feel natural now, even though they represent a dramatic shift from how humans lived for most of their existence. One of the most striking examples of electricity's quiet role is lighting. Artificial light has extended the day far beyond natural limits. It allows work, leisure, and social activity to continue regardless of the sun's position. Yet modern lighting systems are so efficient and unobtrusive that they rarely draw attention to themselves. A room is simply bright or dim. The process that converts electrical energy into light, whether through heating a filament or exciting electrons in a semiconductor, happens instantly and invisibly. The same is true for sound. Music, voices, and ambient noise are all often mediated by electrical systems. Microphones convert vibrations in the air into electrical signals. Speakers reverse that process, turning electrical changes back into sound waves. This translation happens so smoothly that the boundary between physical sound and the electronic reproduction becomes difficult to notice. A conversation over a phone feels direct, even though it depends on layers of electrical processing, transmission, and reconstruction. Screens provide another example. They are everywhere, yet they rarely invite reflection on how they function. Images appear stable and continuous, but they are composed of countless tiny elements that respond to electrical signals at high speed. Colors change, motion appears fluid, and information updates instantly. The electricity driving these changes does not behave like a visible flow. It manifests as controlled differences in voltage, timed pulses, and coordinated responses across millions of components. Because electricity works at such small scales, its effects can feel detached from physical reality. Pressing a button does not feel like applying force in the traditional sense. There is no resistance, no visible connection between effort and result. The cause and effect relationship is still there, but it has been abstracted. This abstraction makes electrical systems feel effortless, which further encourages them to fade into the background of awareness. The quiet presence of electricity is also reinforced by standardization. Electrical outlets look similar across rooms and buildings. Devices are designed to work within specific ranges of voltage and frequency. Cables, plugs, and connectors follow conventions that make compatibility predictable. All of this reduces friction. When systems are standardized, they require less thought. When they require less thought, they attract less attention. Yet this apparent simplicity rests on a complex foundation. Behind every outlet is a network of wires, transformers, and control systems that manage the flow of energy. Electricity does not arrive at the point of use by chance. It is generated, transmitted, adjusted, and monitored continuously. The reason this process feels invisible is not because it is trivial, but because it has been refined to operate without interruption. The moment electricity fails, that invisibility disappears. A power outage instantly reveals how many systems depend on electrical continuity. Lights go out, devices shut down, heating and cooling systems stop responding. The silence that follows is not just the absence of sound, but the absence of activity. Suddenly, actions that were automatic require alternative methods, or cannot be performed at all. The contrast between normal operation and absence highlights how deeply electricity is woven into daily life. This dependence extends beyond obvious devices. Transportation systems rely on electricity for signaling, scheduling, and increasingly for propulsion. Water treatment and distribution depend on electrically powered pumps and monitoring equipment. Food preservation relies on refrigeration. Healthcare depends on electrically powered diagnostic tools, monitoring systems, and life support equipment. Even activities that seem purely physical often depend on electrical infrastructure operating quietly in the background. Despite this, electricity is rarely perceived as a single, unified system. It is experienced as a series of localized interactions. You turn on a lamp, you charge a phone, you heat food. Each interaction feels separate, even though they are all connected to the same underlying network. This fragmentation of experience makes it harder to appreciate the scale and coordination involved in making electricity consistently available. Another reason electricity feels quiet is that it does not usually require human judgment in real time. Mechanical systems often need adjustment. Fires need tending. Water flows need monitoring. Electrical systems, once designed and installed, often operate automatically. Sensors, switches, and control circuits respond faster than human reflexes ever could. The result is a sense that electricity takes care of itself. This autonomy is not accidental. It reflects a long history of engineering aimed at reducing risk and increasing reliability. Electricity can be dangerous if uncontrolled, so systems are designed to limit exposure, isolate faults, and shut down safely when problems arise. Circuit breakers, insulation, grounding, and protective devices all contribute to making electricity feel benign. When these systems work as intended, electricity loses its sense of threat and becomes another assumed feature of the environment. The quiet role of electricity also shapes behavior. People adapt routines around electrically powered tools without consciously planning to do so. Meals are timed around appliances. Work is organized around devices and connectivity. Leisure activities depend on powered entertainment. Over time, these adaptations become habits, and habits rarely draw attention to their underlying causes. This has consequences for how electricity is valued. Because it is so reliable, it can be taken for granted. Its absence feels disruptive, but its presence feels normal. This can make it difficult to appreciate the effort required to produce and distribute electrical power, or the resources involved. Electricity is often discussed in terms of consumption rather than creation, which further distances everyday experience from the physical reality of energy generation. There is also a psychological dimension to electricity's quiet presence. Humans are good at filtering out constant stimuli. Background noise fades, familiar environments blur. Electricity, by being constant, becomes part of that filtered background. It is noticed only when it changes, when it fails, or when it behaves unexpectedly. This selective attention is not a flaw. It is a feature of how perception works. But it does shape how electricity is perceived and discussed. In many ways, electricity functions like a shared language between devices. It allows components to communicate, coordinate, and respond. This communication is silent, fast, and precise. Signals move as variations in voltage or current, encoding information in patterns that machines can interpret. To a human observer, nothing appears to move, yet decisions are being made, states are being updated, and actions are being triggered. This silent communication has enabled levels of complexity that would be difficult to manage mechanically. Modern systems often involve millions or billions of electrical interactions per second. Trying to observe or control these interactions directly would be impossible. Instead, humans interact with interfaces that translate complex electrical behavior into simple choices. Buttons, touchscreens, and icons act as intermediaries, hiding complexity behind familiarity. As a result, electricity becomes less about understanding and more about trust. People trust that when they press a switch, the light will turn on. They trust that devices will behave predictably. This trust is built through experience, not explanation. It does not require knowledge of electrons or circuits. It requires consistency. Yet beneath that consistency lies constant movement. Electrical charge does not rest. Even when devices appear idle, electrons are responding to fields, maintaining potentials, and standing ready to move when conditions change. The stillness of electrical systems is an illusion created by balance. As long as forces are equal and pathways are intact, nothing noticeable happens. Change occurs only when that balance is altered. This idea of balance is central to understanding why electricity can be both omnipresent and unobtrusive. Systems are designed to maintain stable states, voltage levels are regulated, currents are limited, fluctuations are smoothed out. All of this contributes to an experience where electricity feels calm and predictable, even though it involves countless charged particles in motion. The quiet presence of electricity is also tied to scale. At the human level, effects are immediate and localized. At the infrastructure level, electricity operates across vast distances. Power generated far away arrives almost instantly at the point of use. This compression of distance further hides the work involved. There is no sense of travel time. Energy does not feel like it has come from somewhere else. It simply appears where it is needed. This can create a disconnect between cause and effect. Flipping a switch does not reveal a power plant ramping up production. Charging a device does not reveal turbines spinning or chemical reactions occurring. The separation between generation and use is both physical and perceptual. Electricity bridges that gap so effectively that the bridge itself becomes invisible. As electricity becomes more integrated into daily life, its quiet presence continues to expand. Objects that were once purely mechanical now contain sensors and circuits. Doors, thermostats, watches, and even light bulbs increasingly rely on electronics. This integration blurs the line between powered and unpowered objects. Electricity becomes less of a feature and more of a default assumption. This shift has implications for how people relate to the physical world. When so many interactions are mediated by electrical systems, the experience of cause and effect becomes less tactile. Actions feel lighter, less physically demanding. This can make technology feel intuitive, but it can also make its foundations harder to grasp. Electricity enables this abstraction by handling complexity silently. Understanding this quiet presence does not require technical mastery. It begins with noticing patterns. How often electricity responds instantly, how rarely it demands attention, how deeply routines depend on it. These observations set the stage for deeper questions about what electricity actually is, how it behaves, and why it can be controlled so precisely. Because while electricity may feel passive in everyday life, it is anything but simple. Its reliability is the result of careful study, experimentation, and design. Its quietness is the product of systems built to remove friction and uncertainty, and its ubiquity reflects a long process of learning how to guide something invisible into forms that serve human needs. As these systems continue to evolve, electricity's role will likely become even less noticeable at the surface level, even as it becomes more essential underneath. Devices will become smaller, faster, and more interconnected. Interactions will feel more seamless, and the movement of charge that makes all of this possible will continue to happen quietly, just out of sight, shaping daily life without asking for attention. To understand how that became possible, it helps to step back from the present moment and look at a time when electricity was not yet a constant companion, when its effects were rare enough to feel surprising, and when people were only beginning to notice that something unusual was happening when certain materials behaved in unexpected ways. Long before electricity became something that flowed predictably through wires, long before it was measured, stored, or sold, it existed only as an encounter. People did not use electricity in the way we understand it now. They experienced it as a sudden event, something that appeared briefly, powerfully, and without invitation. It arrived as a flash in the sky, a sting in the hand, or a strange attraction between objects that otherwise seemed ordinary. These encounters were rare enough to be memorable and confusing enough to invite explanation, even when no clear explanation was available. The most dramatic of these encounters was lightning. Few natural phenomena command attention the way a lightning strike does. It announces itself with light intense enough to turn night into day and sound loud enough to be felt through the ground. It arrives without warning, travels faster than the eye can follow, and vanishes just as quickly. For early humans, lightning was not just a spectacle. It was a force capable of starting fires, splitting trees, killing animals, and reshaping landscapes. It demanded respect long before it invited understanding. Lightning did not look like anything else in the natural world. It did not behave like fire, even though it could cause burning. It did not behave like wind, even though it moved through the air. It seemed to come from the sky itself, descending with intent, often during storms that already felt chaotic and threatening. It is not surprising that many early cultures associated lightning with gods, spirits, or supernatural power. When a phenomenon is both powerful and unpredictable, it tends to acquire meaning beyond its physical effects. Despite this, lightning also sparked curiosity. People noticed patterns. Storms followed certain weather conditions. Lightning tended to strike tall or isolated objects. Fires caused by lightning behaved like fires caused by other means. These observations did not immediately lead to scientific explanations, but they did lay the groundwork for noticing that lightning was part of the natural world, not entirely separate from it. Another early encounter with electrical effects came not from the sky, but from the ground, in the form of certain materials that behaved strangely when handled. One of the most notable was amber. Amber is fossilized tree resin, often warm to the touch and capable of holding a polish. When rubbed with fur or cloth, amber can attract small bits of straw, dust, or hair. This attraction is gentle but noticeable, and it persists briefly after the rubbing stops. To someone unfamiliar with the electrical behavior, this effect is puzzling. The amber does not appear sticky. There is no visible force connecting it to the objects it attracts, and yet the objects move, as if pulled by something unseen. Unlike lightning, this effect is quiet and subtle. It does not demand attention, it rewards close observation. The attraction of amber was noticed thousands of years ago. It was one of the earliest recorded examples of what we now call static electricity. At the time, it was simply a curiosity. Amber seemed to possess a temporary ability to influence other objects. This ability faded with time, which only added to the mystery. Whatever was happening did not leave a lasting mark. Other materials exhibited similar behavior. Glass, sulfur, and certain stones could also attract light objects after being rubbed. These effects were inconsistent and difficult to reproduce without specific conditions, which made them hard to study systematically. Without instruments to measure charge or fields, early observers relied entirely on their senses. What made these effects significant was not their usefulness, but their challenge to ordinary expectations. Objects that were not alive, not magnetic, and not visibly adhesive were nonetheless exerting influence at a distance. This contradicted everyday experience, where contact was usually required to cause motion. The idea that objects could affect one another without touching raised questions that had no easy answers. Early explanations often relied on analogies. Some thinkers imagined invisible vapors or fluids being transferred during rubbing. Others suggested that materials absorb something from the air. These ideas were speculative, but they reflected a genuine attempt to make sense of observed behavior using the conceptual tools available at the time. It is important to remember that curiosity does not require precision. Early investigations into electrical effects were exploratory rather than controlled. People noticed what happened, tried variations, and shared observations. The lack of a formal framework did not prevent learning. It shaped the kind of learning that occurred. Lightning and amber represented two extremes of the same underlying phenomenon. One was violent, large-scale, and destructive. The other was gentle, small-scale, and harmless. At the time, there was no reason to believe they were related. They appeared in different contexts, behaved differently, and carried different meanings. It would take centuries before anyone seriously proposed that they were manifestations of the same kind of force. Between these extremes were other encounters that hinted at a broader pattern. Certain fish, now known to produce electric discharges, were known to cause shocks when touched. These shocks were unpleasant and sometimes painful. but they were not accompanied by heat or visible injury. This made them difficult to classify. They were not bites, stings, or poisons. They were something else entirely. People who encountered these fish described the sensation as sudden and penetrating. The effect travelled through the body rather than staying localised at the point of contact. This suggested that whatever was causing the sensation could move through flesh, not just along surfaces. Again, this challenged ordinary assumptions about how forces behaved. Over time, these various encounters accumulated as isolated facts. There was lightning in the sky. There were strange attractions between rubbed materials. There were shocks from certain animals. Each phenomenon was interesting on its own. The challenge was recognizing that they might share a common cause. Part of what delayed that recognition was the lack of a unifying concept. Electricity, as a word and as an idea, did not yet exist in a meaningful way. There was no single category to place these effects into. Without that category, there was no reason to compare them directly. Another obstacle was scale. Lightning operates on a scale that dwarfs human activity. Static attraction operates on a scale that is easy to miss. The idea that the same underlying behaviour could produce both seemed unlikely. It required a willingness to think across orders of magnitude, something that was not common in early natural philosophy. Even so, curiosity persisted. People continued to observe, record, and speculate. Over time, certain patterns became harder to ignore. Rubbing materials produced effects that resembled, in miniature, the suddenness of lightning. Shocks from fish felt similar, in a small way, to the jolt of a lightning strike experienced indirectly. These resemblances were not precise, but they were suggestive. As methods of inquiry became more formal, especially in later centuries, these observations began to be treated less as curiosities and more as subjects for systematic study. But in the early period, before wires and instruments, progress was slow and uneven. Knowledge advanced through storytelling as much as experimentation. Accounts of strange effects circulated, sometimes exaggerated, sometimes misunderstood. What mattered was not accuracy in the modern sense, but accumulation. Each observation added to a growing body of experience that challenged simple explanations of the natural world. Electricity, though not yet named or understood, was quietly asserting its presence. The absence of wires is significant here. Wires would later become the defining feature of electrical systems, guiding charge along predictable paths. Without wires, electrical effects were fleeting and difficult to contain. They appeared and disappeared, leaving no lasting structure behind. This made them feel less like tools and more like events. Because of this, early encounters with electricity were often framed in terms of agency. Lightning struck, amber attracted, fish shocked. The language implied action, as if the objects themselves were doing something intentionally. This is a natural way to describe phenomena that do not yet have a mechanical explanation. Over time, as understanding grew, this language would change. Agency would be replaced by mechanism. But in the early period, curiosity was expressed through stories, metaphors, and analogies rather than equations. It is also worth noting that early curiosity about electrical effects did not exist in isolation from other forms of inquiry. It was part of a broader effort to understand nature. The same thinkers who pondered lightning and amber were also studying motion, heat, sound, and light. Electricity was one thread in a larger tapestry of questions about how the world works. What set electricity apart was its resistance to classification. It did not fit neatly into existing categories. It was not a substance in the usual sense. It did not have a fixed form. It could appear as light, force, or sensation depending on circumstances. This ambiguity made it both frustrating and fascinating. As centuries passed, these early encounters would be revisited with new tools and new perspectives. Experiments would become more controlled. Concepts would become more precise. Connections would be drawn that were previously invisible. But all of that rested on the willingness of early observers to notice something strange and ask why it behaved the way it did. Before wires, electricity was not a system, it was a series of clues. Each lightning strike, each attracted fragment of straw, each unexpected shock added another piece to a puzzle that no one yet knew how to assemble. The curiosity that drove people to notice these effects did not depend on knowing where it would lead. It depended on paying attention. That habit of attention, once established, would eventually transform electricity from a mysterious occurrence into something that could be studied, named, and manipulated. But that transformation required a shift from seeing electricity as an occasional surprise to seeing it as a consistent behaviour governed by rules. That shift did not happen all at once. It began slowly, with small questions and tentative connections, and it set the stage for a deeper exploration of what electricity actually is, beyond lightning and amber, beyond shock and attraction, as something rooted in the structure of matter itself. To talk about what electricity actually is, it helps first to clear away what it is not. Electricity is not a substance that gets poured into devices. It is not a kind of fuel that is burned up when something turns on, and it is not a mysterious fluid sloshing through wires, even though that image has been used for centuries because it feels intuitive. Electricity is better understood as organised behaviour. It is the coordinated movement and interaction of charged particles, governed by rules that are consistent, measurable, and surprisingly strict once you know where to look. At the foundation of electricity is the atom. Everything around you, solid, liquid, or gas, is made of atoms arranged in different ways. Atoms themselves are not solid little balls. They are structures, with a dense centre called a nucleus, and much lighter particles moving around it. In the nucleus are protons and neutrons. Protons carry a positive electric charge. Neutrons carry no charge at all. Around the nucleus are electrons, which carry a negative electric charge. That word, charge, is doing a lot of work here, but it does not need to be mysterious. Electric charge is simply a property of particles that determines how they interact with one another. Particles with the same kind of charge push each other away. Particles with opposite charges pull toward each other. That's it. There is no hidden intention behind it. It is just how these particles behave. In most everyday objects, electric charges balance out. The number of positively charged protons is equal to the number of negatively charged electrons. When charges are balanced like this, there is no overall electrical effect that you can notice from the outside. The object is electrically neutral. This is the default state of most matter, and it is why electricity often feels absent until something changes. Electricity appears when that balance is disturbed. If electrons are moved from one place to another, suddenly you have regions where charge is not balanced. One area has extra electrons and becomes negatively charged. Another area is missing electrons and becomes positively charged. Nature does not like this imbalance. The attraction between opposite charges creates a tendency for electrons to move back toward balance. That movement, when it is allowed to happen in a controlled way, is what we call electricity in action. This is where the idea of flow comes in, but it needs to be handled carefully. In many electrical systems, electrons do move through materials, especially metals, but the important part is not that individual electrons travel long distances like runners on a track. The important part is that changes propagate through a system. When an electrical circuit is completed, the effect of electron shifting happens almost everywhere at once, even though each electron itself moves quite slowly. Imagine a long line of people standing shoulder to shoulder. If the person at one end steps forward slightly, everyone in the line adjusts. The motion travels quickly through the line, even though no single person moves very far. Electricity behaves in a similar way. The signal moves fast. The individual particles move only a little. This distinction matters because it helps explain why electricity can feel instantaneous. When you flip a switch, the light turns on almost immediately. That does not mean electrons have raced from a power plant to your lamp at incredible speed. It means the electrical system was already full of charge carriers, ready to respond. Closing the switch changes the conditions, and the system adjusts nearly at the speed at which electrical influences propagate. Another important idea is that electricity is not just about movement, but about potential. Electrical systems are often described in terms of differences: a difference in charge, a difference in energy, a difference in electrical pressure, which is what voltage represents. Voltage is not electricity itself. It is the condition that encourages electricity to happen. If two places have the same electrical potential, nothing moves between them. If there is a difference, charges will try to move in a way that reduces that difference. Electricity is the process of that movement under constraints. Those constraints are provided by materials, geometry, and design. Materials matter a great deal. Some materials allow electrons to move easily. These are called conductors. Metals are good examples. In metal, some electrons are not tightly bound to individual atoms. They can move through the material relatively freely when conditions allow. Other materials hold onto their electrons much more tightly. These are insulators. Rubber, glass, and many plastics fall into this category. They do not easily allow charge to move through them. This difference between conductors and insulators is not arbitrary. It comes from how atoms are arranged and how electrons are shared or confined within those arrangements. You do not need to know the quantum mechanics behind it to understand the practical result. Some materials support electrical movement, others resist it. Modern electrical systems are built around that distinction. Electricity, then, is not a thing that exists on its own. It is an activity that occurs when charged particles are allowed or encouraged to move in certain ways. When those movements are restricted or balanced, electricity becomes quiet. When they are directed, electricity becomes useful. This perspective helps unify many of the electrical phenomena that once seemed unrelated. Static electricity, for example, is just charge imbalance without a continuous path for movement. When you rub a balloon on your hair, electrons are transferred from one material to another. The charges stay separated because there is no easy route for them to recombine. When they finally do, often suddenly, you feel a spark or a shock. Lightning is the same process on a much larger scale. Charge builds up in clouds due to collisions between particles in turbulent air. The ground below becomes oppositely charged. The imbalance grows until the attraction becomes strong enough to overcome the insulating properties of air. When that happens, electrons surge across the gap. The result is a lightning strike. Different scale, same underlying behavior. Electric current, the kind that powers devices, is simply charge moving continuously through a path. That path is a circuit. A circuit is not defined by the presence of electricity. It is defined by the ability to support ongoing movement. When a circuit is complete, charge can move in a loop. When it is broken, movement stops. This idea of looping is important. Electricity in most systems does not start at one point and disappear at another. It circulates. Energy is transferred, but charge is conserved. Electrons are not consumed by devices. They move, interact, and return. What gets used up is energy, not charge. Energy enters the picture because moving charges can do work. They can transfer energy to other systems. They can make a filament glow, push a motor, transmit information, or trigger chemical reactions. Electricity is a way of moving energy from one place to another, using charge as the carrier. This is why electricity is so versatile. The same underlying process can be used for heating, lighting, motion, computation, and communication. The difference lies in how the movement is arranged and what it interacts with along the way. It also explains why electricity must be carefully controlled. Unrestricted movement of charge can release energy too quickly, causing damage or danger. Controlled movement allows energy to be delivered at useful rates. Everything from resistors to switches exists to manage how charge moves and how much energy is transferred. One reason electricity feels abstract is that it is not a single phenomenon. It is a category that includes many related behaviors. Static charge, current, field, signals, and energy transfer are all part of the same picture, but they show up differently depending on context. When people say electricity, they're often referring to the useful end result rather than the underlying process. Another source of confusion is direction. Historically, electrical current was defined before electrons were discovered. As a result, current is said to flow from positive to negative, even though electrons actually move from negative to positive. This mismatch does not affect how systems work, but it can make explanations feel contradictory. The key point is that what matters is consistency, not the chosen convention. Electricity is also inseparable from electric fields. An electric field is not a thing you can hold. It is a description of how charged particles influence the space around them. When a charge is present, it alters the conditions nearby in a way that affects other charges. Fields allow forces to act at a distance without direct contact. You do not need to imagine fields as physical objects. Think of them as a bookkeeping tool that tells you what would happen if a charge were placed somewhere. Electricity depends on these fields to guide movement and interaction. When a circuit operates, electric fields inside the conductor help organize how electrons respond. This field-based view helps explain why electricity can act quickly over distances. Changes in fields propagate through space, carrying information about changing conditions. The charges respond to these changes locally, but the coordination happens through the field. At no point does electricity require awareness or intent. It follows rules automatically. If the conditions are right, charge moves. If they are not, it stays put. The apparent intelligence of electrical systems comes from design, not from electricity itself. Humans create pathways, set conditions, and define limits. Electricity does the rest. Understanding electricity in this way removes much of its mystery without removing its importance. It is not magical, it is systematic, but it is also subtle. Its effects depend on arrangements that are not obvious without careful thought. That combination of simplicity and subtlety is what made electricity so difficult to grasp historically, and so powerful once understood. When you strip away the jargon, electricity is about imbalance seeking balance, guided by structure. It is about charges responding to differences, moving when they are allowed, stopping when they are not. Everything else, the terminology, the units, the equations, exist to describe that behavior with precision. As we move forward, this core idea will keep resurfacing. Whether we're talking about batteries, generators, or living cells, the same principles apply. Charges are separated. Conditions encourage movement. Energy is transferred. Systems respond. With that foundation in place, it becomes easier to understand how humans learned not just to observe electricity, but to store it, summon it, and make it flow on demand, turning a once rare curiosity into something that could be carried, contained, and used whenever needed, whenever. When we talk about electricity at its most basic level, everything narrows down to charge and the particles that carry it. Not devices, not wires, not power stations, but the smallest moving things that make electrical behavior possible in the first place. Understanding this does not require complex mathematics or specialized language. It requires patience and a willingness to think small, much smaller than anything we can see, because electricity is driven by activity at a scale that the human brain did not evolve to notice directly. Every solid object you encounter feels continuous and stable, but at the microscopic level it is mostly empty space. Atoms are separated by distances far larger than their own size, and inside each atom, even more space exists between the nucleus and the electrons around it. This matters because electricity does not involve solid blocks of matter sliding past one another. It involves tiny particles responding to forces across empty space, guided by rules that operate reliably whether or not anyone is watching. Charge is the key property that makes this possible. Charge is not a substance, and not an add-on. It is an intrinsic feature of certain particles, much like mass. A particle either has charge or it does not, and if it does, that charge has a specific sign. There are two kinds of electric charge, which we label positive and negative. These labels are arbitrary, but the behavior they describe is consistent. Like charges repel each other, opposite charges attract. This attraction and repulsion is not conditional. It does not weaken because something is tired or distracted. It follows the same rules everywhere in the universe as far as we can tell. That consistency is what allows electricity to be predictable once the system is understood. In everyday matter, charge is usually balanced. Atoms contain equal amounts of positive and negative charge, which cancel out overall. This balance is why most objects do not behave electrically most of the time, but the balance is not rigid. Electrons, which carry negative charge, are comparatively light and loosely held in many materials. Protons, which carry positive charge, are locked into atomic nuclei and do not move freely under ordinary conditions. This difference in mobility is crucial. Nearly all everyday electrical behavior involves electrons, not protons. When charge moves in a wire, it is electrons shifting position. When static electricity builds up, it is electrons being transferred from one surface to another. When a spark jumps, it is electrons finding a sudden path back toward balance. Electrons are remarkably small. They have mass, but it is tiny compared to the mass of protons and neutrons. Because of this, electrons respond readily to forces that would not noticeably affect heavier particles. Electric fields can push and pull electrons with ease, especially in materials where they are not tightly bound to individual atoms. This brings us to an important distinction. Electrons are always present in matter, but they are not always free to move. In some materials, electrons are tightly associated with specific atoms or bonds. In others, particularly metals, some electrons are shared across many atoms. These shared electrons form a kind of flexible population that can respond collectively to changes in electrical conditions. When an electric field is applied to a conductor, these mobile electrons experience a force. They begin to drift. The word drift is important here because it captures the actual scale of the motion. Electrons in a wire move slowly, often at speeds measured in millimeters per second. This surprises many people because electrical effects happen so quickly. The speed of electrical response does not come from fast-moving electrons travelling long distances. It comes from the near-instantaneous adjustment of electric fields throughout the system. When conditions change, electrons everywhere respond locally. The overall effect propagates rapidly, even though each electron moves only a short distance. This is why thinking of electricity as a stream of particles flowing from a source to a device can be misleading. The electrons powering your lamp were already in the wire before you turned it on. What changed was not their existence, but the conditions that allowed them to move in an organized way. Charge, then, is not just something particles have. It is something particles respond to. Charged particles influence each other even when they are not in direct contact. This influence is described by electric fields, which extend through space and define how a charge would behave if it were present at a particular location. Electric fields are not physical objects. They are descriptions of influence, but they are essential for understanding how electricity operates without direct contact. When charges rearrange themselves, the electric field changes and other charges respond accordingly. This coordination allows electrical systems to function as unified wholes, rather than as collections of independent particles. At the smallest scales, this interaction becomes probabilistic rather than deterministic. Electrons do not follow neat classical paths like tiny balls rolling along a track. Their behavior is governed by quantum mechanics. They occupy regions rather than precise points. They respond to forces in ways that can only be predicted statistically. The details of quantum mechanics are complex, but the practical outcome is straightforward. Electron behavior is consistent enough, when averaged over large numbers, to produce reliable electrical effects. A wire contains an enormous number of electrons. Their individual uncertainties average out, leaving stable, predictable behaviour at the human scale. This averaging is what allows engineers to treat electricity as smooth and continuous, even though it arises from discrete particles. It is similar to how a crowd can move smoothly, even though each person takes individual steps. At large scales, the motion appears fluid. Another important particle in this story is the ion. An ion is an atom or molecule that has gained or lost one or more electrons. When an atom loses an electron, it becomes positively charged. When it gains an electron, it becomes negatively charged. Ions play a major role in many electrical systems, especially in liquids, gases, and biological environments. In solids like metals, electrons are the primary charge carriers. In liquids, such as salt water, ions carry charge by moving through the solution. In gases, ions and free electrons can both contribute to electrical conduction under the right conditions. This diversity of charge carriers allows electricity to appear in many different forms. The smallest moving things in electrical systems are not always electrons alone. Sometimes entire atoms or molecules move, carrying charge with them. This happens in batteries, where chemical reactions cause ions to migrate between different regions. It happens in biological systems, where ions move across cell membranes to transmit signals. Despite these differences, the underlying principle remains the same. Charged particles move in response to forces created by charge imbalances. The details vary, the scale varies, the medium varies, but the core behaviour does not change. One reason this can be difficult to grasp intuitively is that charged particles respond to fields, not to intentions. They do not know where they are going in a human sense. They follow local rules. If the field pushes them one way, they move. If it pushes the other way, they move differently. Complex behaviour emerges from simple responses repeated across enormous numbers of particles. This is why electricity can be both simple and powerful. The rules are few, the outcomes are vast. By arranging materials and shapes in particular ways, humans have learned to guide these simple interactions into systems capable of remarkable precision. It is also why electricity is sensitive to disruption. Small changes in conditions can alter how particles move. Temperature affects how easily electrons scatter. Impurities in materials change how charge carriers behave. Structural defects influence pathways. Electrical systems must account for these factors to remain stable. At the smallest scale, motion is never perfectly smooth. Electrons collide with atoms. Ions bump into molecules. Energy is lost as heat. Resistance is the macroscopic expression of these microscopic interactions. It is not a barrier placed in the way of electricity. It is a description of how particle motion is hindered by the environment. Understanding this helps demystify why electrical systems heat up. When charge carriers move, they transfer energy to the material they move through. That energy appears as increased motion of atoms, which we perceive as heat. This is not a failure of the system. It is an inevitable consequence of particle interactions. The fact that electricity relies on the smallest moving things also explains why it can be so precisely controlled. By shaping materials at microscopic and even atomic scales, it is possible to influence how electrons behave. This is the basis of modern electronics, where tiny structures guide charge with extraordinary accuracy. Semiconductors, for example, are materials engineered to have very specific electrical properties. Their behaviour depends on how electrons and missing electrons, called holes, move through carefully designed regions. By controlling these movements, devices can amplify signals, store information, and perform logical operations. All of this rests on the same fundamental idea. Charged particles respond to forces. They move when allowed. They stop when constrained. The complexity comes not from the particles themselves, but from the structures built to guide them. At this scale, time also behaves differently from how we experience it. Particle interactions happen incredibly fast. Electric fields adjust almost instantly. Signals propagate at significant fractions of the speed of light, yet the cumulative effects unfold at human timescales that feel manageable and familiar. This mismatch between microscopic speed and macroscopic experience contributes to the sense that electricity is both immediate and distant. You see the result instantly, but the process itself remains hidden, compressed into a timescale that feels like zero. Despite this invisibility, the behavior of charged particles leaves measurable traces. Voltages, currents, and fields are all ways of summarizing collective particle behavior. They do not replace the particles. They describe what the particles are doing in aggregate. Keeping this in mind prevents a common misunderstanding. Electricity is not an abstract force floating above matter. It is inseparable from the particles that carry it. Remove the particles, and electricity disappears. Rearrange the particles, and electricity changes. As we continue forward, this particle-level view will keep grounding the discussion. Whether electricity is flowing through a wire, stored in a battery, or signaling between neurons, the same smallest moving things are at work. They're always responding to imbalance, always interacting through fields, always constrained by their environment. The remarkable thing is not that electrons move, it is that humans learned how to arrange matter so that their movement could be predicted, guided, and repeated reliably. That achievement depends on understanding charge not as an abstract idea, but as a property of real particles doing real work at scales too small to see. Once that understanding began to take shape, it opened the door to the next step in the story. If charge could move, and if that movement could be guided, then the natural question became how to make it move continuously, not just in brief, accidental bursts, but in steady, controlled ways that could be used again and again. Static electricity is often treated as a minor curiosity, a harmless annoyance that makes hair stand up or delivers an unexpected sting when you touch a metal surface. But historically, static electricity was one of the first ways humans began to move from vague curiosity toward genuine understanding. It was electricity slowed down enough to be noticed, repeated, and questioned. Unlike lightning, which was overwhelming and rare, static electricity could be produced deliberately, observed closely, and compared across situations. That made it an ideal doorway into learning how electrical effects actually behave. At its core, static electricity is about charge separation that stays in place, at least temporarily. When two different materials come into contact and then separate, electrons can transfer from one to the other. This does not happen randomly. It depends on the properties of the materials involved. Some materials hold onto electrons more tightly, others give them up more easily. When they touch, electrons shift. When they separate, that shift remains. One object ends up with an excess of electrons and becomes negatively charged. The other ends up with a deficit and becomes positively charged. Because the charges are not free to move back into balance, they remain stuck, building up electrical potential. Nothing dramatic happens right away. There is no flow, no circuit, no continuous movement. The electricity is there, but it is static. It waits. This waiting is what makes static electricity feel different from the electricity that powers devices. It is stored in balance rather than organized motion. But that stored imbalance still exerts influence. Charged objects attract or repel other charged objects. They can pull neutral objects toward them by subtly rearranging charges inside those objects. They can distort electric fields in the space around them. Early observers noticed these effects without knowing why they happened. A rubbed piece of amber attracting bits of straw was not just a trick. It was evidence that contact could alter an object's ability to influence its surroundings. This influence did not require heat, moisture, or visible residue. It was invisible and transient, which made it difficult to classify. As experiments became more deliberate, patterns emerged. Rubbing was important. Separation mattered. Dry conditions made effects stronger. Moist air weakened them. Materials behaved differently from one another. None of this made sense within existing frameworks of explanation, but the consistency of the observations suggested that something systematic was happening. The word static comes from the idea of standing still, and that is an accurate description of what is happening most of the time. The charges are separated, but they cannot easily move. The materials involved act as insulators, preventing electrons from flowing freely. As a result, charge accumulates. This accumulation creates tension, not emotional tension, but physical imbalance. Opposite charges attract strongly. The longer the imbalance persists, the stronger the attraction becomes. Eventually, if a path becomes available, the charge will move suddenly to restore balance. That sudden movement is what produces a spark or a shock. The shock itself is brief, but it is informative. It reveals that electricity can be stored and released. It reveals that air, which normally acts as an insulator, can become conductive under the right conditions. It reveals that electrical effects are not limited to gentle attractions, but can involve rapid, energetic motion. For someone encountering this without modern context, a static shock is a striking experience. It arrives without warning. It feels localized yet penetrating. It leaves no visible mark but demands attention. The fact that it can be produced intentionally makes it especially intriguing. Unlike lightning, which cannot be summoned on demand, static shocks can be repeated. This repeatability is crucial. Science advances when phenomena can be reproduced. Static electricity allowed early experimenters to test ideas, vary conditions, and compare results. It turned electricity from a rare spectacle into a manipulable effect. One of the key realizations that emerged from these experiments was that electricity could exist without continuous motion. It could be present as stored imbalance. This was a departure from earlier ways of thinking about forces, which often focused on motion as the defining feature. Static electricity showed that potential mattered just as much as movement. Another realization was that electricity could jump gaps. A spark leaping through air demonstrated that electrical effects were not confined to solid materials. This challenged the assumption that contact was always necessary for interaction. Electricity could bridge empty space if the conditions were right. These sparks were small compared to lightning, but they followed similar rules. They produced light, heat, and sound. They followed jagged paths. They occurred suddenly once a threshold was reached. This resemblance hinted at a deeper connection, even if it was not yet fully understood. Static electricity also revealed the importance of environment. Dry air allowed charge to build up more easily. Humidity provided pathways for charge to leak away. This explained why shocks were more common in certain seasons or conditions. It also showed that electricity was sensitive to surroundings, not just to materials. As understanding grew, people began to build devices specifically to generate and study static electricity. These early machines were simple in principle. They used mechanical motion to rub materials together repeatedly, accumulating charge. Glass discs, belts, and pads were arranged to maximize contact and separation. The goal was not power, but control. With these devices, experimenters could store larger amounts of charge and release it more dramatically. Leyden jars, early capacitors, allowed charge to be accumulated and held. When discharged, they produced strong shocks that could be felt through the body. These experiences were sometimes used in public demonstrations, blending education with spectacle. While this might sound theatrical, it played an important role in spreading awareness of electrical behavior. People could feel electricity directly. They could see sparks and hear snaps. Electricity became something tangible rather than abstract. At the same time, these experiments raised questions. Why did some materials charge more easily than others? Why did charge sometimes leak away? Why did shocks vary in intensity? Answering these questions required thinking beyond surface effects and considering what might be happening at smaller scales. Gradually, the idea of charge as a transferable property took shape. Electricity was no longer just an effect. It was something that could be gained, lost, stored, and released. This conceptual shift was essential. It allowed electricity to be treated as a quantity, even before precise measurement was possible. Static electricity also introduced the idea of polarity. Objects could be charged in different ways, leading to attraction or repulsion. This duality was not just a curiosity, it suggested symmetry and balance, concepts that would become central to later electrical theory. Another important insight was that neutral objects could be influenced by charged ones. This showed that electricity could rearrange charge within materials without transferring it outright. This effect, now known as polarization, explained why charged objects could attract neutral ones. It also hinted at the internal structure of matter. At the time, atoms were not yet understood in detail, but these observations pushed thinkers toward the idea that matter had internal components that could shift relative to one another. Electricity was not acting on solid blocks. It was acting on something more flexible inside them. The limitations of static electricity were also instructive. Charge buildup had natural limits. Discharge was sudden and hard to control. There was no easy way to make static electricity do continuous work. These limitations highlighted the difference between potential and sustained motion. Static electricity could shock, attract, and spark, but it could not easily turn wheels, light rooms, or transmit information reliably. This was not a failure of understanding, but a clue. It suggested that another form of electrical behavior existed, one that involved continuous flow rather than stored in balance. The contrast between static electricity and flowing electricity would later become central to the development of electrical technology. But before that distinction was clear, static electricity served as the training ground. It familiarized people with key ideas: charge, imbalance, attraction, discharge, and the role of materials. It also revealed that electricity obeyed rules. The effects were not random. They depended on conditions that could be manipulated. This predictability encouraged further exploration. Importantly, static electricity bridged the gap between everyday experience and abstract theory. You could feel it. You could see it. You could cause it to happen. That sensory connection grounded later, more theoretical work. As understanding deepened, static electricity stopped being mysterious in the mythological sense and started being mysterious in a scientific sense. The question shifted from what caused these effects to how they worked. This shift marks the beginning of true electrical science. Even today, static electricity retains its teaching role. It is often the first electrical phenomenon people experience consciously. A shock from a doorknob, clothes clinging together, a balloon sticking to a wall. These experiences are simple, but they embody the same principles that govern vast electrical systems. They remind us that electricity does not require wires or machines to exist. It arises naturally whenever charge is separated and constrained. The same forces that power cities are at work in these small, familiar moments. Understanding static electricity also helps demystify more complex systems. It shows that dramatic effects can arise from simple imbalances. It shows that energy can be stored invisibly and released suddenly. It shows that the environment matters. As the story of electricity continues, static electricity represents an early chapter of learning, one defined by touch and surprise rather than calculation. It was through these first shocks, literal and intellectual, that humans began to see electricity not as an isolated curiosity, but as a consistent behavior rooted in the smallest moving parts of matter. From there, the natural next question emerged. If electricity could be stored and released, could it be made to move continuously, not just in brief sparks, but in a steady, controllable way that could be harnessed again and again? For a long time, electricity revealed itself only in brief moments. A spark jumped. A shock was felt. A bit of straw lifted and fell back again. These events were striking, but they were fleeting. They appeared, discharged, and vanished. What they lacked was continuity. And without continuity, electricity could not easily be put to work. The turning point in the story of electricity came when people stopped asking how to make sparks and started asking how to make electricity move steadily, not as a sudden release, but as an ongoing process. This shift in thinking was subtle but profound. A spark is electricity escaping. A current is electricity being guided. The difference lies not in the particles themselves, but in the conditions surrounding them. To move from sparks to currents, humans had to learn how to separate charge and then provide it with a controlled path back toward balance, one that did not collapse immediately. At the heart of this challenge was the idea of a circuit. A circuit is not a device. It is a condition. It exists when there is a complete loop that allows charged particles to move continuously. Without a loop, electricity builds up and then stops. With a loop, electricity can keep going as long as the conditions that drive it remain in place. This may sound obvious now, but it was not obvious at the time. Early experiments with electricity often focused on generating charge, not on sustaining motion. Rubbing materials, spinning glass discs, and building up static charge were all effective at producing sparks, but they did not naturally lead to continuous flow. Every discharge reset the system. To go further, something new was needed. That something was a source of sustained imbalance. Static electricity relied on temporary separation of charge created by friction. What was needed was a way to maintain a difference in electrical potential without constant mechanical intervention. In other words, electricity needed a steady push. This push does not come from electricity itself. Electricity does not decide to move, it responds to differences. If one part of a system has higher electrical potential than another, charge particles will tend to move in a way that reduces that difference. If the difference is maintained, the movement continues. The earliest steps toward continuous flow came from chemical processes. Certain chemical reactions naturally involve the movement of electrons from one substance to another. In these reactions, electrons are not just shuffled briefly, they are transferred as part of a stable process. By separating the parts of such a reaction and connecting them externally, it became possible to encourage electrons to move through a wire instead of directly between substances. This was the essential insight behind early batteries, though the word battery would come later. These early devices did not produce sparks in the dramatic sense. They produced something quieter but far more useful. They produced a steady electrical current. A current is simply charge in motion through a conductor, but the simplicity of that definition hides an important distinction. A current is not about how much charge exists. It is about how much charge moves over time. This introduces time as a central element. Electricity was no longer just something that happened, it became something that endured. Once current was possible, everything changed. Electricity could now do work continuously. It could heat wires steadily rather than briefly. It could cause chemical changes to proceed at controlled rates. It could produce magnetic effects that lasted as long as the current flowed. This last point turned out to be especially important. When electricity flows, it creates a magnetic influence around the conductor. This connection between electricity and magnetism was not immediately understood, but it was observable. A compass needle deflected near a current-carrying wire. The effect was consistent and repeatable. Here again, continuity mattered. A brief spark did not produce a lasting magnetic effect. A steady current did. This opened the door to a new class of experiments and eventually to new technologies that depended on the interaction between electricity and magnetism. But before those developments could unfold, people had to learn how to manage current itself. Unlike static electricity, which announces itself with sparks and shocks, current is quiet. It flows without drama. This quietness makes it more dangerous in some ways, because it can deliver energy continuously, without obvious warning signs. Controlling current required understanding resistance. Resistance is not a substance or an obstacle placed in the way of electricity. It is the result of interactions between moving charges and the material they move through. As electrons drift through a conductor, they collide with atoms and imperfections. These collisions slow the movement and convert some electrical energy into heat. Every material resists electrical flow to some degree. Even good conductors offer resistance. This resistance determines how much current will flow for a given difference in potential. By choosing materials and shapes carefully, it became possible to regulate current, preventing it from becoming too large or too small. This regulation was essential. Too much current can overheat materials, damage structures, or cause injury. Too little current may not produce useful effects. Learning to balance these factors turned electricity from a curiosity into a practical tool. Another key realization was that current requires a closed path. If the path is broken, current stops. This seems obvious now, but early experimenters had to learn it through trial and error. Electricity does not leap gaps indefinitely. It follows paths of least resistance, and those paths must connect back to the source. This idea of closure is what gives switches their power. A switch does not create electricity. It does not store electricity. It simply opens or closes a path. When the path is closed, current flows. When it is open, current stops. The simplicity of this action belies its importance. It allows humans to control electricity with minimal effort. As currents became easier to generate and control, people began to notice differences between types of current. Some currents flowed steadily in one direction, others reversed direction periodically. These differences were not immediately important, but they would later shape how electrical systems were designed and used. At this stage, what mattered most was the realization that electricity did not have to be explosive or unpredictable. It could be calm, steady, and reliable. It could be measured, adjusted, and repeated. This realization shifted the cultural perception of electricity. It stopped being associated primarily with danger and spectacle, and began to be associated with utility. Making electricity flow also required better conductors and connections. Loose contacts, impurities, and irregular shapes could disrupt current. Experimenters learned that smooth, continuous paths produced better results. This led to improvements in wire materials, insulation, and connectors. Insulation was just as important as conduction. To guide current effectively, it had to be confined to intended paths. Materials that prevented charge from leaking away became essential. Without insulation, currents dissipated and control was lost. The pairing of conductors and insulators is a defining feature of electrical systems. As systems grew more complex, the idea of branching paths emerged. Electricity could be directed to multiple destinations. It could be split, combined, and routed. This required thinking about how current distributes itself through networks. Electricity does not divide arbitrarily. It follows rules based on resistance and potential differences. Understanding these rules allowed for the design of circuits that behaved predictably. Lamps could be added without extinguishing others. Devices could be connected without interfering with one another. This predictability was crucial for scaling up electrical use. The move from sparks to currents also changed how electricity was measured. Static electricity was difficult to quantify. Currents, by contrast, could be compared, timed, and standardized. This led to the development of units and instruments that made electrical behavior more concrete. Measurement reinforced understanding. When something can be measured, it can be tested against expectation. When it can be tested, theories can be refined. The feedback loop between observation and explanation accelerated progress. There is also a psychological dimension to this transition. Sparks are exciting but uncooperative. Currents are less dramatic but more dependable. Human societies tend to build around dependability. Once electricity could be made to flow steadily, it became something that could support daily activities rather than interrupt them. This transition mirrors a broader pattern in technology. Many natural phenomena are first encountered as hazards or curiosities. Only later are they domesticated, controlled, and integrated into routine life. Fire followed this path. So did electricity. Importantly, making electricity flow did not mean eliminating sparks altogether. Sparks still occur under certain conditions, especially when current is interrupted abruptly or when insulation fails. But sparks became exceptions rather than the norm. They were signs of something going wrong, not the primary goal. As electrical currents became more familiar, new questions emerged. How strong could a current be? How far could it travel? How could it be generated without relying on chemical reactions alone? These questions would lead to new methods of producing electricity involving motion and magnetism. But at this stage, the essential breakthrough had already occurred. Electricity had been transformed from a momentary event into a continuous process. That transformation required understanding charge, imbalance, pathways, and resistance. It required thinking in loops rather than lines, in systems rather than isolated effects. Once that way of thinking took hold, electricity became something that could be designed around. Circuits could be planned, outcomes could be predicted, failures could be diagnosed. Electricity entered the realm of engineering, and with that shift, electricity began to move out of laboratories and demonstrations and into practical use. It started to power experiments, tools, and eventually entire systems. The quiet flow of current replaced the sharp crack of sparks as the defining sound of electrical activity. This did not mean that the mystery was gone. Many aspects of electrical behavior were still poorly understood. But the foundation had been laid. Electricity could flow, and once it could flow, it could be shaped, amplified, redirected, and transformed in ways that would soon extend far beyond simple circuits into realms where electricity would begin to interact with motion itself, opening the door to an even deeper layer of connection between invisible charge and the physical world. Before electricity could become a constant companion, before it could be summoned at will with a switch or routed across landscapes, there had to be a way to keep it available even when nothing else was moving. Sparks were brief. Currents needed encouragement. What electricity lacked early on was patience. It needed a way to wait. Batteries provided that, not as magic containers of electricity, but as systems that quietly held imbalance in place, ready to release it in a controlled way. To understand batteries is to understand how motion can be stored without anything visibly moving at all. A battery is often described as something that contains electricity, but that description is misleading. A battery does not store electricity in the way a tank stores water. What it stores is chemical energy arranged so that electrons are encouraged to move in a particular direction when given a path. The electricity does not exist as a flow until the circuit is completed. Until then, the battery is a system under tension, holding potential rather than motion. This idea of stored motion can feel counterintuitive. Motion usually implies activity, change, something happening. But in batteries, motion is prepared rather than expressed. The ingredients are positioned in such a way that movement is favoured but restrained. The moment restraint is lifted, motion begins. At the heart of every battery is a chemical reaction. More specifically, a set of reactions that involve electrons being transferred between substances. Some materials are more willing to give up electrons, others are more eager to receive them. When these materials are placed in contact, electrons move directly from one to the other, and the reaction proceeds until equilibrium is reached. If that were all that happened, there would be no battery, just chemistry. The crucial step is separation. In a battery, the parts of the reaction are kept apart physically. They are connected only through an external path. This forces electrons to travel through that path if they are to move at all. That path is where electricity appears. Inside the battery, one region becomes rich in electrons, the other becomes deficient. This separation creates a difference in electrical potential. As long as the separation is maintained, the potential remains. The battery is charged not because electrons are circulating, but because they are prevented from doing so directly. This prevention is deliberate. It is the defining feature of a battery. By controlling how and where electrons are allowed to move, chemical energy is converted into electrical energy in a usable form. The chemistry does the work of pushing electrons uphill against the natural tendency toward balance. The circuit allows them to flow back down in a controlled way. The simplest batteries illustrate this principle clearly. Two different metals placed in a suitable chemical environment can form a basic battery. One metal tends to lose electrons more readily, the other tends to gain them. When connected externally, electrons flow from one to the other through the wire. Inside the battery, chemical reactions replace the electrons that leave and accommodate the electrons that arrive, keeping the process going. What makes this process stable is that the chemical reactions proceed gradually. They do not release all their energy at once. They operate at a rate determined by material properties, temperature, and design. This gradual release is what makes batteries safe and useful rather than explosive. The term voltage describes how strongly a battery pushes electrons. It reflects the difference in electrical potential created by the chemical arrangement inside. A higher voltage means a stronger push, not necessarily more energy overall. Energy capacity depends on how much chemical material is available to sustain the reaction. This distinction explains why small batteries can have the same voltage as large ones, but deliver energy for a much shorter time. The push is the same, the duration is different. Once the chemical reactants are exhausted or rearranged into a lower energy state, the battery is depleted. The stored motion has been spent. From the outside, a battery looks static. There are no moving parts, nothing spins or vibrates, and yet, internally, particles are constantly interacting. Ions migrate through internal structures, electrons accumulate at one terminal and are depleted at the other. Chemical bonds are broken and formed. Motion is everywhere, just not in ways that are easy to see. This invisibility contributed to the early mystery of batteries. When the first practical batteries were demonstrated, they seemed almost magical. They could produce steady currents without friction, heat, or obvious activity. Compared to mechanical generators, which demanded visible effort, batteries felt self-contained and effortless. But that effort was simply hidden in chemistry. The energy stored in a battery ultimately comes from chemical bonds, which themselves are products of earlier energy inputs. In rechargeable batteries, that input is electrical energy supplied from elsewhere. In disposable batteries, it comes from the energy invested during manufacturing. Rechargeable batteries add another layer to the story. In these systems, the chemical reactions can be reversed. When current is forced through the battery in the opposite direction, electrons are pushed back into their original positions. The chemical imbalance is restored. The battery is charged again. This reversibility is not perfect. Each cycle introduces inefficiencies. Some energy is lost as heat. Materials degrade over time, but the basic principle holds. Motion can be stored, released, and stored again, not as electricity itself, but as chemical potential ready to become electricity. Understanding batteries also clarifies an important point about electricity in general. Electricity is not a source of energy, it is a carrier. Batteries are sources of energy because they contain chemical systems capable of doing work. Electricity is the means by which that work is delivered elsewhere. This distinction matters because it prevents a common misunderstanding. Plugging a device into a battery does not pull electricity out of the battery like liquid. It completes a pathway that allows chemical energy inside the battery to be converted into electrical energy and then into whatever form the device uses. The internal design of batteries determines how smoothly this conversion happens. Inside most batteries is a medium that allows ions to move but blocks electrons. This internal separator ensures that electrons must travel through the external circuit, not directly between the battery's internal regions. Without this separation, the battery would short-circuit internally and discharge uselessly. The materials chosen for batteries reflect trade-offs. Some chemistries offer high energy density but degrade quickly. Others are more stable but heavier or bulkier. Some can deliver high currents rapidly. Others are better suited for slow, steady output. These differences explain why different devices use different kinds of batteries. From a conceptual perspective, all of these designs share the same foundation. They use chemistry to hold charge apart, to maintain imbalance and to release that imbalance gradually. The details change, the principle does not. Batteries also introduce the idea of portability to electricity. Before batteries, electricity was tied to specific setups. Static machines had to be operated. Early generators required motion. Batteries allowed electricity to be carried. This mobility changed how electricity was used and imagined. With batteries, electricity no longer had to be produced at the moment of use. It could be prepared in advance. This decoupling of generation and use is one of the most important steps in the history of electrical technology. It made electricity flexible. That flexibility also encouraged experimentation. With a battery, you could power circuits repeatedly, test configurations, and observe behavior over time. The reliability of battery-powered currents made it easier to study electrical effects systematically. Batteries also reinforced the idea of direction in electrical systems. Electrons move from one terminal to the other through the circuit. Reversing the connections reversed the direction of current. This directional behavior would later become important in understanding how electricity interacts with other phenomena. There is also a temporal aspect to batteries that is easy to overlook. A battery does not release all its energy instantly. It releases it over time. This makes time an intrinsic part of how batteries function. Power, the rate at which energy is delivered, becomes just as important as total energy. A battery powering a small device for many hours is delivering energy slowly. The same battery powering a large device may deliver energy quickly and deplete rapidly. The chemistry allows both. The difference lies in how the circuit draws current. This responsiveness is another reason batteries feel intuitive. They adjust to demand within limits. They do not force energy into a system that cannot accept it. They respond to conditions set by the external circuit. At the same time, batteries are constrained. Draw too much current and internal heating increases. Chemical reactions speed up or become unstable. Design limits are reached. These constraints remind us that batteries are physical systems, not abstract sources. Thinking of batteries as stored motion helps unify these ideas. The motion is potential until a path is provided. The rate of motion depends on resistance. The duration depends on capacity. The efficiency depends on internal losses. Nothing about this is arbitrary. This perspective also connects batteries to earlier electrical ideas. Static electricity stored in balance without useful continuity. Batteries stored in balance with a controlled pathway ready to be used. The difference lies in structure, not in the fundamental nature of charge. As battery technology improved, it enabled new forms of electrical experimentation and application. Continuous currents could now be produced anywhere, not just near mechanical setups. This independence accelerated discovery. But batteries also revealed limitations. Chemical energy, while convenient, is finite and must be replenished or replaced. As electrical systems grew larger and more demanding, batteries alone were not sufficient to supply them. This limitation prompted another question. If electricity could be produced from chemical reactions, could it also be produced from motion directly, without consuming materials in the process? Could movement itself be turned into a steady electrical push? That question would lead electricity into a new phase of its development, one where motion and magnetism would intertwine, and where stored chemical imbalance would no longer be the only way to keep electrons moving. For a long time, electricity and magnetism lived separate lives in human understanding. Electricity crackled, sparked, shocked, and flowed. Magnetism pulled, aligned, and pointed. One belonged to lightning and amber, the other to lodestones and compasses. They were studied by different people, used for different purposes, and described with different language. There was no obvious reason to think they were connected. And yet, Once electricity learned how to move steadily, magnetism quietly stepped into the story and refused to leave. Magnetism had been familiar for centuries before electricity was ever controlled. Certain rocks, naturally magnetized iron minerals, could attract small pieces of metal. Even more strangely, they could influence one another at a distance, aligning north to south in consistent ways. When a magnet was suspended freely, it pointed in a particular direction, a direction that turned out to be tied to the Earth itself. This property made magnetism practical long before it was understood. Compasses guided travellers, sailors, and explorers across land and sea, long before anyone knew why they worked. Like early electricity, magnetism felt selective. Not all materials responded. Wood, stone, and cloth were unaffected. Iron and steel behaved differently, snapping toward magnets with visible enthusiasm. This selectivity made magnetism feel like a special force, something limited and contained rather than universal. Magnets also seemed permanent. Unlike static electricity, which faded, magnetism could persist. A magnet could sit on a table for years and still attract metal just as strongly. This permanence gave magnetism an air of stability that electricity lacked in its early encounters. Because of this, magnetism developed its own identity. It was not thought of as stored electricity or frozen lightning. It was its own phenomenon, governed by its own rules. And for a long time, that separation made sense. The bridge between electricity and magnetism appeared only after electricity learned how to flow continuously. A spark was too brief to leave a lasting mark. A steady current, however, created conditions that could be observed over time. This continuity made subtle effects visible. When experimenters placed a compass near a wire carrying a steady electrical current, something unexpected happened. The compass needle moved. It did not point toward the wire. It did not flee from it. Instead, it deflected sideways, as if responding to an invisible influence wrapping around the wire itself. This deflection was small, but it was unmistakable. More importantly, it was repeatable. Turn the current on, and the needle moved. Turn it off, and the needle returned to its original position. Reverse the direction of the current, and the needle deflected in the opposite direction. This behavior could not be explained by existing ideas about electricity or magnetism alone. Electricity had not been known to influence compasses. Magnetism had not been associated with flowing charge. Something new was happening. The implication was profound. Moving electric charge created a magnetic effect. Magnetism was not just a property of certain materials, it could arise from electrical motion itself. This realization collapsed a boundary that had existed for centuries. Electricity and magnetism were not separate phenomena after all. They were different aspects of the same underlying behavior. What made this discovery especially powerful was that it was not subtle once understood. Any steady current produced a magnetic influence. The effect did not depend on special materials or rare conditions. It depended only on motion. This magnetic influence was not concentrated at a point. It formed a pattern around the conductor. If you could see it, it would appear as a set of circular tendencies surrounding the wire. The compass needle was not being pulled toward the wire. It was responding to this surrounding influence. That surrounding influence is what we now call a magnetic field. Like electric fields, magnetic fields are not objects. They are descriptions of influence. They tell us how magnetic or moving charge particles would behave if they were present at a given location. The important point is that magnetic fields arise naturally from moving charges. You do not need a magnet to have magnetism. You need motion. This idea immediately raised new questions. If moving charge creates magnetism, could magnetism create moving charge? Could the relationship work both ways? The answer turned out to be yes, but not in the most obvious way. Magnetism does not push electrons directly the way an electric field does. Instead, changes in magnetic conditions can encourage electrons to move. This distinction matters. A steady magnetic field does not produce a current on its own. but a changing magnetic field can. This asymmetry is subtle, but essential. Imagine a loop of wire. If a magnet is held still near the loop, nothing happens. But if the magnet is moved toward or away from the loop, an electrical current appears briefly in the wire. Reverse the motion, and the current reverses direction. Once again, continuity mattered. It was not magnetism alone that caused electricity to flow. It was change. Motion, either of charge or of magnetic conditions, was the key. This revealed a deeper symmetry. Electricity in motion produces magnetism. Changing magnetism produces electricity. The two phenomena were not just related, they were intertwined. This connection transformed magnetism from a curiosity into a tool. If moving charge created magnetism, and magnetism could influence moving charge, then electricity could be shaped and controlled in new ways. One immediate consequence was the ability to produce magnetism on demand. By sending current through a wire coiled into a loop, the magnetic influence became stronger and more concentrated. Wrap the wire around an iron core and the effect intensified further. The result was an electromagnet. Unlike permanent magnets, electromagnets could be turned on and off. Their strength could be adjusted by changing the current. Their polarity could be reversed. This flexibility made them vastly more useful than natural magnets. Electromagnets demonstrated something crucial. Magnetism was not a fixed property. It could be created, shaped, and controlled by electrical conditions. This realization laid the groundwork for machines that relied on the interplay between electricity and motion. At the same time, magnetism provided a new way to visualize electrical behavior. Electric current itself was invisible, but its magnetic effects could be detected with compasses, iron filings, and later instruments. Magnetism made electricity visible indirectly. This visibility helped refine understanding. It showed that current did not simply move from one point to another in isolation. It affected the space around it. Electrical systems extended beyond wires. They shaped their environment. Magnetism also introduced directionality in a new way. Electric fields push charges along a line. Magnetic influences wrap around motion, producing forces that act sideways relative to movement. This difference would later become essential for understanding motors and generators. The interaction between electricity and magnetism also clarified why earlier phenomena behaved the way they did. Lightning, for example, is not just an electrical discharge. It is a massive, fast-moving current. That current produces intense magnetic effects, even though they are rarely noticed because the event is so brief. Static electricity, by contrast, produces little magnetism because there is little sustained motion. Once charge stops moving, magnetic effects disappear. This distinction reinforced the idea that electricity has different modes of existence. Stored imbalance behaves differently from flowing current. Motion changes everything. As experiments continued, magnetism stopped being an isolated subject and became part of electrical theory. Descriptions that once applied only to magnets now applied to current-carrying conductors. The language began to merge. It also became clear that magnetism was not limited to iron. Any moving charge contributed. Iron simply made magnetic effects easier to detect because its internal structure responded strongly to magnetic conditions. This insight dissolved another misconception. Magnets did not attract iron because iron contained magnetism. Iron responded because its internal charges and magnetic domains could align with an external magnetic influence. Magnetism was not inside the iron in a mystical sense. It was imposed upon it. Understanding this made magnetism feel less mysterious and more systematic. Like electricity, it followed rules. It depended on motion and arrangement. It could be predicted. The entry of magnetism into the story of electricity also expanded the scale of what electricity could do. With magnetism, electricity could now produce motion. A current in a magnetic field experiences a force. arrange conductors and magnets properly, and electrical energy can be converted into mechanical motion. This conversion would soon become central to technology. But even before machines were built, the principle was clear. Electricity and magnetism together formed a loop of influence. Motion created fields. Fields guided motion. This loop was not optional, it was fundamental. Electricity could no longer be understood without magnetism, and magnetism could no longer be understood without electricity. Importantly, this unification did not eliminate earlier ideas, it built on them. Charge, imbalance, current, and resistance still mattered. Magnetism added another layer, another dimension of interaction. It also introduced the idea that forces could be perpendicular to motion, not just aligned with it. This challenged intuitive notions of cause and effect, and required new ways of thinking about direction and geometry. As these ideas settled, electricity ceased to be just a way of delivering energy. It became a way of shaping motion itself. Electrons could be guided not only along wires, but through space of influence defined by magnetic conditions. This expanded perspective set the stage for the next transformation. If electricity and magnetism together could produce motion, then motion itself might be used to produce electricity, not chemically, not statically, but mechanically, by harnessing movement in the physical world. That realization would take electricity out of the laboratory and into the landscape, linking it to spinning coils, turning shafts, flowing water, and moving steam, and turning the quiet interaction between charge and magnetism into the backbone of large-scale power generation. Electricity had learned how to wait inside batteries, and it had learned how to flow steadily through circuits, but it still depended on stored chemical imbalance to get started. That dependence imposed limits. Batteries could be carried, but they ran out. Chemical reactions could be reversed, but only so many times. If electricity was going to grow beyond small experiments and portable devices, it needed a more abundant source of encouragement. That source turned out to be motion itself. Not the motion of electrons this time, but the motion of larger objects in the physical world. Generators are where electricity stopped relying primarily on chemistry and began drawing directly from movement. The idea behind a generator is simple in principle, even if the details take time to appreciate. If changing magnetic conditions can cause electric charges to move, then moving something through a magnetic influence, or moving a magnetic influence past something, should create electricity. This is not about sparks or shocks. It is about steady, repeatable motion producing steady, repeatable electrical flow. What makes generators powerful is not that they create energy. They do not. They convert energy from one form into another. The energy already exists as motion, often rotational motion, and the generator's role is to turn that motion into organized electrical activity. At the center of this conversion is a loop of conductive material, usually wire. When that loop experiences a changing magnetic environment, electrons inside the wire are encouraged to move. The movement does not come from nowhere. It comes from the work done to change the magnetic conditions. That work requires force. That force comes from whatever is driving the motion. Imagine a loop of wire placed between the poles of a magnet. If nothing moves, nothing happens. The magnetic conditions are stable. The electrons in the wire feel no net encouragement to drift in one direction. But if the loop is rotated, the situation changes. Different parts of the loop experience different magnetic influences over time. The balance shifts continuously. Electrons respond by moving. A current appears. This current does not last forever on its own. It exists only as long as the motion continues. Stop the rotation, and the current stops. The generator does not store electricity. It produces it moment by responding to ongoing motion. This dependency on motion explains why generators are so closely tied to turbines. A turbine is simply a device designed to spin when something flows past it. That something might be water, steam, gas, or air. The turbine's job is to capture kinetic energy from that flow and convert it into rotational motion. Water flowing downhill carries energy because of gravity. Steam carries energy because of heat. Wind carries energy because of pressure differences in the atmosphere. Turbines are shaped to extract a portion of that energy efficiently, turning it into rotation that can be coupled to a generator. Once rotation is available, the generator takes over. Coils move through magnetic fields. Magnetic fields move past coils. The distinction depends on design, but the outcome is the same. Electrical current is produced. One of the most important features of generators is that they produce electricity continuously, as long as motion continues. There is no need to rebuild charge through friction or chemical reactions. The process is smooth, repeatable, and scalable. Scale matters here. Early electrical experiments involved tiny currents and small devices. Generators made it possible to produce large amounts of electricity by increasing the size of the system or the speed of rotation. Bigger turbines, stronger magnetic influences, and more coils all contributed to higher output. This scalability is why generators became central to electrical infrastructure. They could be built large enough to supply entire cities. They could be driven by natural processes that were already occurring on vast scales, such as rivers flowing or steam expanding. The first practical generators were not immediately efficient. Early designs lost energy to friction, heat, and imperfect materials, but even inefficient generators demonstrated something transformative. Electricity could be produced anywhere motion could be harnessed. This freed electricity from the constraints of chemistry. Instead of relying on stored materials that would eventually be depleted, electricity could now be tied to ongoing processes. As long as something kept moving, electricity could keep flowing. That realization shifted how energy itself was understood. Motion was no longer just something electricity caused, it became something electricity depended on. The relationship went both ways. Turbines in this context are not electrical devices, they are mechanical intermediaries. Their role is to take chaotic or diffuse motion, like flowing water or expanding steam, and turn it into orderly rotation. Order matters because generators respond best to predictable, continuous motion. The design of turbines reflects this goal. Blades are shaped to extract energy gradually rather than abruptly. Sudden changes waste energy and cause damage. Smooth flow produces smooth rotation, which produces stable electrical output. Different energy sources require different turbine designs. Water turbines are shaped differently from steam turbines. Wind turbines are optimized for airflow rather than dense fluids. But the underlying principle remains consistent. Capture motion, turn it into rotation, feed it into a generator. Once electricity is produced by a generator, it behaves like any other current. It flows through circuits, encounters resistance, and transfers energy to whatever is connected downstream. The generator does not care what happens after that, as long as the load does not exceed its capacity. However, there is an important feedback effect. When a generator supplies current to a load, it becomes harder to turn. The flowing current creates magnetic effects that oppose the motion that produced it. This is not a design flaw. It is a consequence of energy conservation. In practical terms, this means that supplying electrical power requires mechanical effort. The more electricity drawn, the more force must be applied to keep the generator spinning at the same speed. This is why power plants must regulate input energy carefully. Demand on the electrical side affects the mechanical side. This coupling between electrical output and mechanical resistance makes generators honest systems. They cannot produce electricity without cost. The cost is paid in the form of mechanical work supplied by turbines, engines, or other movers. This also explains why large-scale electricity production is tied to large-scale energy sources. Rivers, fossil fuels, nuclear reactions, and wind patterns all provide sustained energy flows that can be converted into motion. That motion is what generators tap into. Generators also introduced a new kind of regularity to electricity. Early battery-powered currents were steady in one direction. Generators often produce currents that reverse direction periodically as coils rotate. This alternating behaviour arises naturally from rotational motion. As a loop rotates through a magnetic influence, the direction of the induced current changes. Half a turn later, the conditions are reversed. The electrons respond accordingly. The result is a current that oscillates rather than flows in a single direction. This oscillation is not a problem. In fact, it turned out to be an advantage. Alternating currents are easier to transform, transmit, and distribute over long distances. But that realization would take time to develop. At this stage, what mattered most was reliability. Generators could run for long periods. Turbines could be driven continuously. Electricity could be produced at scales far beyond what batteries could supply. This reliability changed how electricity was perceived. It was no longer an experimental phenomenon or a laboratory curiosity. It became a service, something that could be delivered on demand as long as the underlying motion continued. The presence of generators also made electricity feel less mysterious. Sparks and shocks faded into the background. The dominant sound of electricity became the hum of rotating machinery, rather than the crackle of discharge. That hum reflected stability. It reflected systems designed to operate for years, even decades, with careful maintenance. Electricity was no longer something that happened. It was something that ran. The relationship between turbines and generators also highlighted the importance of efficiency. Every step in the conversion process introduced losses: friction in bearings, turbulence in fluids, electrical resistance in coils, all consumed energy without producing useful output. Reducing these losses became a major focus. Better materials, improved designs, and tighter tolerances all contributed. The goal was not perfection, which is unattainable, but predictability and control. As generators improved, they became more compact and more powerful. Smaller generators could produce more electricity than earlier larger ones. This allowed electricity production to spread beyond centralized locations. Portable generators appeared. Vehicles began to carry their own electrical sources driven by engines. Remote locations could generate electricity without direct connection to a large grid. At the same time, very large generators were built for centralized production. Massive turbines driven by steam from burning fuel or from nuclear reactions produced electricity at scales that could support millions of people. This duality, small generators for local use and large generators for centralized supply, is a direct result of the flexibility of the generator concept. It does not depend on a specific energy source, it depends on motion. This flexibility also allowed electricity to adapt to different environments. Where rivers were abundant, water turbines dominated. Where fuel was available, steam turbines took over. Where wind was reliable, wind turbines emerged. In every case, the generator sat at the boundary between the mechanical world and the electrical world. On one side, physical motion. On the other, moving charge. The generator translated between them continuously. Understanding generators also helps clarify a subtle but important point. Electricity is not created at power plants in the same way water is drawn from a well. Electricity is generated dynamically. It exists because motion is happening right now. This means that electricity supply must constantly match demand. If demand increases, more mechanical effort is required. If demand decreases, effort must be reduced. The system is always balancing. This balancing act would later become one of the defining challenges of electrical infrastructure. But even at this stage, it was clear that electricity tied to motion was not passive. It required coordination. Generators made electricity abundant but not effortless. They shifted the problem from storing charge to managing motion. Instead of worrying about chemical depletion, engineers now worried about mechanical wear, fuel supply, and system stability. This shift was transformative. It allowed electricity to grow beyond the scale of individual experiments and devices and become a backbone of society. Once electricity could be generated reliably from motion, The next challenge was not production, but delivery. How could electricity produced in one place be transported efficiently to many other places, sometimes far away, without losing too much along the way? Answering that question would require new decisions about how electricity should move, not just within machines, but across entire regions, leading directly into debates about different kinds of current and how best to move electrical energy over distance. Once electricity could be generated reliably from motion, a new problem came into focus almost immediately. It was no longer enough to make electricity, it had to be moved. Electricity produced by generators was often far from where it was needed, and getting it from one place to another without wasting too much energy became one of the central challenges of the electrical age. This challenge exposed a fundamental divide in how electricity could behave while moving, a divide that would shape electrical systems ever since. At the centre of this divide were two different ways electricity could flow. One involved charge moving steadily in a single direction. The other involved charge reversing direction over and over again. Both were forms of current. Both followed the same underlying rules of charge and motion, yet they behaved very differently when pushed beyond small local systems. Direct current, often shortened to DC, is the simpler of the two to describe. In a direct current system, electrons drift consistently in one direction around a circuit. The push that drives them does not change direction. Batteries naturally produce this kind of current. Chemical reactions inside a battery separate charge in a fixed orientation, and when a circuit is completed, electrons move predictably from one terminal to the other. This steadiness makes direct current intuitive. It matches the early mental model of electricity as something that flows like a stream. It also makes DC well suited for devices that require stable, predictable conditions. Early electrical experiments, powered by batteries, relied almost entirely on direct current. When generators entered the picture, direct current was the first form of generated electricity to be widely used. Early generators were designed to mimic the behaviour of batteries, producing current that flowed in a single direction. This was achieved through mechanical switching built into the generator, which redirected the electrical output as the generator rotated. At small scales, this worked well enough. Lamps could be lit, motors could be driven, electrical demonstrations became practical. For a time, it seemed reasonable to assume that direct current would form the backbone of electrical infrastructure. But problems began to appear as systems grew larger. The most significant issue was distance. Sending electricity over long distances is not trivial. As current moves through a conductor, it encounters resistance. That resistance converts some electrical energy into heat. The longer the distance, the more energy is lost. This loss depends on two main factors: how much current is flowing and how resistant the conductors are. Resistance is set by material and geometry. Current depends on how much power is being delivered and at what electrical pressure or voltage. For a given amount of power, higher current means more loss, lower current means less loss. This leads to a simple but powerful insight. If you want to move electrical energy efficiently over long distances, you want to keep current as low as possible. The problem with direct current was that changing voltage levels was difficult. Early DC systems operated at fixed voltages. If you wanted to deliver power at a higher voltage to reduce current, you needed different generators or complex machinery. There was no simple, efficient way to adjust voltage up and down. As a result, DC power had to be distributed at relatively low voltages. Low voltage meant high current. High current meant significant energy loss over distance. This limited how far DC power could travel economically. Alternating current, or AC, approached the problem differently. In an AC system, the direction of current reverses periodically. Electrons move back and forth rather than drifting steadily in one direction. The frequency of this reversal is fixed by the system design. At first glance, this back and forth motion seems inefficient. If electrons are constantly reversing direction, how can useful work be done? The answer lies in the fact that many electrical processes depend not on net movement of electrons across long distances, but on the transfer of energy through coordinated motion. AC may cause electrons to oscillate locally, but the energy associated with that motion can travel efficiently through the system. More importantly, alternating current made it easy to change voltage levels using simple electromagnetic devices. These devices, known as transformers, rely on changing magnetic conditions. When an AC current flows through a coil, it creates a changing magnetic influence. That changing magnetic influence can induce a current in a nearby coil. By adjusting the number of turns in each coil, voltage can be increased or decreased with minimal energy loss. This ability to transform voltage was a breakthrough. It meant electricity could be generated at 1 voltage, transmitted at a much higher voltage to reduce losses, and then stepped down again to safer levels for use in homes and businesses. Direct current could not do this easily. Alternating current could, and could do it efficiently and reliably. This single advantage outweighed many of AC's apparent complexities. The divide between AC and DC was not just technical. It became economic and philosophical. Different engineers, inventors, and investors favoured different approaches. Some argued for the simplicity and familiarity of direct current. Others emphasised the scalability and efficiency of alternating current. What mattered most, however, was not ideology, but infrastructure. Once power networks began to expand beyond small areas, the practical benefits of AC became difficult to ignore. High-voltage transmission allowed electricity to travel far from where it was generated. Power plants no longer had to sit next to consumers. Electricity could be centralized and distributed widely. Alternating current also aligned naturally with generator design. Rotational motion in generators naturally produces alternating electrical conditions. Producing AC directly was simpler than producing DC and then converting it. Direct current generators required additional mechanical components to straighten out the output. These components added complexity, wear, and inefficiency. AC generators avoided this by letting the alternating nature of rotation translate directly into electrical output. Another advantage of AC was its compatibility with motors. Electric motors convert electrical energy back into mechanical motion. AC motors, in particular, proved to be robust, simple, and durable. They required fewer components and less maintenance than many early DC motors. This does not mean direct current disappeared. DC has properties that make it valuable in specific contexts. Batteries produce DC naturally. Electronic devices often require DC internally. Certain industrial processes benefit from steady unidirectional current. But as a backbone for large-scale distribution, AC had clear advantages. It allowed electricity to become a shared resource across cities, regions, and eventually entire countries. The phrase Great Electrical Divide reflects how consequential this choice was. Once an electrical system is built around a particular kind of current, switching becomes expensive and disruptive. Power plants, transmission lines, transformers, motors, and appliances all depend on the nature of the current they are designed to handle. When AC became dominant for distribution, it set standards that still shape electrical systems today. Frequencies were chosen, voltage levels were standardized. Infrastructure grew around those decisions. It is worth emphasizing that alternating current does not mean chaotic or unpredictable current. The reversals happen at precise, regular intervals. This regularity is what makes AC manageable. The system behaves like a rhythm rather than a random oscillation. From a user's perspective, this rhythm is invisible. Lights glow steadily, motors turn smoothly, devices operate without flicker or interruption. The back and forth motion happens too quickly to notice. Direct current, by contrast, feels conceptually simpler, but requires more infrastructure to achieve the same flexibility. Modern power systems often involve both forms. AC is used for long-distance transmission. DC is used locally within devices after conversion. This coexistence reflects a deeper truth. AC and DC are not competing philosophies. They are tools suited to different roles. The divide mattered historically because one had to be chosen as the foundation for large systems. Once that choice was made, the other found its place within it. Understanding this divide also clarifies why electrical systems look the way they do. The presence of transformers, substations, and transmission towers is a direct consequence of choosing AC. The presence of adapters, rectifiers, and power supplies in devices reflects the need to convert AC back into DC for electronics. None of this is accidental. It is the outcome of balancing physical laws, economic constraints, and practical needs. The debate was never about which current was better in an abstract sense. It was about which one allowed electricity to reach more people with fewer losses. Once that decision settled, electricity could finally stretch across landscapes. Power stations could be placed near fuel sources or natural energy flows. Cities could grow without being bound to local generators. Electricity became a network rather than a collection of isolated systems. This networked nature of electricity introduced new challenges. Synchronization, safety, and reliability became critical. Systems had to agree on frequency. Failures had to be isolated. Loads had to be balanced continuously. But those challenges only existed because electricity had crossed the threshold from local phenomenon to shared infrastructure. The choice between alternating and direct current made that possible. With electricity now capable of travelling far from its source, the next layer of the story shifts from how electricity behaves to how it is organised. How grids are built, how power is routed, how millions of users can draw energy from the same system without it collapsing under the strain. That organisation would turn electricity into something larger than any single generator or turbine, transforming it into a coordinated living system that spans continents, quietly adjusting itself moment by moment to keep the lights on. Electricity does not appear at your wall socket by accident. By the time it reaches that quiet, unremarkable opening in the wall, it has already taken a long and carefully managed journey. That journey is shaped by one overriding requirement: electricity must be produced, moved, and delivered at the exact moment it is needed. Unlike water or fuel, electricity is not easily stored at large scales. It must be coordinated continuously. Power grids exist to make that coordination possible. A power grid is not a single machine or location. It is a network, layered and distributed, designed to connect sources of electrical generation with millions of points of use. It includes generators, transmission lines, substations, transformers, control systems, and protective devices. Each part plays a role in guiding electrical energy from motion at one end to usefulness at the other. The journey begins where electricity is generated. This might be a hydroelectric dam, a thermal power plant driven by steam, a wind farm spread across a hillside, or another source of rotational motion feeding generators. At these sites, generators produce alternating current at specific frequencies. The electricity produced here is energetic but not yet ready for long-distance travel. Sending electricity directly from generators to distant cities at low voltage would waste enormous amounts of energy. Resistance in wires would turn much of it into heat. To avoid this, electricity is prepared for travel by increasing its voltage. This happens almost immediately after generation. Transformers located near power plants raise the voltage dramatically. Increasing voltage allows the same amount of power to be transmitted with much lower current. Lower current means lower losses. This step does not create energy. It rearranges how energy moves through the system, making long-distance transport practical. Once stepped up, electricity enters the transmission network. These are the high-voltage lines that stretch across landscapes, carried by tall towers or buried underground in some regions. At this stage, electricity is moving efficiently, but it is far from user-friendly. The voltages involved are far too high for direct use. Transmission lines are designed for durability and efficiency. They must withstand weather, temperature changes and mechanical stress while maintaining consistent electrical behaviour. They also operate under constant monitoring. Small changes in load, damage or imbalance can ripple across the network if not managed carefully. One of the defining features of a power grid is that it must stay synchronized. Alternating current systems rely on a shared rhythm. All generators connected to the grid must agree on frequency and phase. If parts of the system fall out of sync, power quality degrades, equipment can be damaged and outages can cascade. Maintaining this synchronization requires continuous adjustment. Power plants respond to demand changes by increasing or decreasing mechanical input. Control systems monitor frequency deviations and correct them by redistributing load. This balancing act happens constantly, often without human intervention. As electricity travels closer to where it will be used, it encounters substations. Substations are nodes in the grid where electricity is transformed, routed, and managed. They are not just stepping stones, they are decision points. At a substation, voltage may be reduced from transmission levels to distribution levels. Electricity may be split across multiple paths, feeding different regions. Protective equipment monitors for faults, isolating damaged sections before they can affect the wider system. The design of substations reflects the need for flexibility. Power demand is not constant. It changes with time of day, weather, and human activity. Substations allow electricity to be redirected as needed, ensuring that supply follows demand. From substations, electricity enters the distribution network. This is the part of the grid that most closely interacts with everyday life. Distribution lines run along streets, through neighbourhoods, and into buildings. The voltages here are lower than transmission levels, but still higher than what individual devices require. Before electricity enters a home or business, it passes through another transformer. This transformer reduces voltage to levels suitable for general use. The familiar outlet voltage is chosen as a compromise between safety and efficiency. Low enough to reduce risk, high enough to deliver useful power without excessive current. By the time electricity reaches the wall socket, it has passed through multiple transformations. Each step was designed to minimize loss, manage risk, and maintain reliability. None of this is visible to the user. The socket simply works. What makes this journey remarkable is not just its length, but its coordination. Electricity flowing into your home is not tagged or reserved for you. It is part of a shared pool. When you turn on a device, you draw energy from the grid, and generators somewhere respond almost immediately by increasing output to compensate. This response does not involve electrons travelling all the way from the generator to your device. The electrons in your home wiring were already there. What changes is the electrical condition of the entire network. The grid adjusts, maintaining balance. This adjustment relies on the grid's ability to sense and react. Sensors throughout the system measure voltage, current, frequency, and phase. Control systems analyze this data and make corrections. In many cases, these corrections happen faster than human operators could respond. The grid is designed to handle disturbances, a tree falling on a line, a generator shutting down unexpectedly, a sudden surge in demand. Protective systems isolate problems, reroute power, and stabilize conditions. This resilience is essential because the grid must operate continuously. Despite this, failures still occur. Power outages reveal the complexity that normally remains hidden. When electricity stops flowing, it is often because multiple protective mechanisms have acted to prevent greater damage. What feels like absence is sometimes the result of systems doing their job. The grid structure also reflects historical and geographical factors. Older systems were built around nearby generation. As transmission improved, grids expanded and interconnected. Today, many regions share power across vast areas, smoothing out local variations in supply and demand. Interconnection increases efficiency and reliability, but it also increases complexity. A problem in one area can propagate if not contained. This is why grid management involves careful planning and constant vigilance. Another challenge is that electricity demand fluctuates constantly. Morning routines, evening lighting, seasonal heating and cooling all create predictable patterns. Unexpected events create unpredictable ones. The grid must be capable of responding to both. To manage this, operators forecast demand and adjust generation accordingly. Some power sources can respond quickly, others take time to ramp up or down. The grid relies on a mix of sources to remain flexible. Renewable energy introduces additional considerations. Wind and sunlight are variable. They cannot be turned on or off at will. Integrating these sources requires additional coordination, storage solutions and responsive systems. Storage at grid scale remains limited, but it is growing. Technologies like pumped hydro, large batteries and other methods help buffer fluctuations. Even so, most electricity is still consumed almost as soon as it is produced. This immediacy makes the grid feel alive. It responds continuously, adjusting itself moment by moment. It is not static infrastructure. It is a dynamic system. Safety is woven into every layer of this journey. High voltages are isolated, faults are detected, systems are grounded. These measures exist because electricity is indifferent to human presence. It follows physical rules without regard for convenience or safety. The grid exists to make those rules work in human environments. By the time electricity reaches your wall socket, it has been shaped, managed, and constrained repeatedly. The socket itself is a carefully designed interface. It provides access while limiting exposure. It invites use while enforcing boundaries. When you plug something in, you complete a local circuit. Electricity flows into your device, does its work, and returns to the grid. The grid absorbs this interaction seamlessly, adjusting elsewhere to maintain balance. This invisibility is the grid's greatest achievement. When it works, it fades into the background. When it fails, it becomes suddenly obvious. That contrast highlights how much coordination is required to make electricity feel ordinary. The long journey to your wall socket is not just a path through space, it is a path through layers of decision-making, engineering, and compromise. Every transformer, every line, every substation exists because electricity behaves the way it does. Understanding this journey does not require memorizing components or diagrams. It requires appreciating that electricity is not just produced and consumed. It is guided, negotiated, and balanced across a system that must respond continuously to human behavior. This system allows electricity to feel immediate, even though it may have been generated far away. It allows millions of people to use power simultaneously without coordination. It allows the flip of a switch to feel personal, even though the response involves machines and processes spread across vast distances. And once electricity arrives at the socket, its journey is not over. Inside devices, it will be shaped again, converted, controlled, and used in increasingly specialized ways, giving rise to machines that depend on electricity not just as energy, but as information and instruction, opening the door to an entirely different relationship between moving charge and modern technology. Once electricity reaches a device, its role changes. Out on the grid, electricity is about delivery and balance. Inside machines, it becomes precise. It stops being a general supply and starts being shaped, timed, and directed for very specific purposes. This is where electricity stops feeling like infrastructure and starts feeling like intelligence, even though nothing about it is thinking. What changes is not electricity itself, but how carefully its movement is controlled. Inside any modern machine, electricity rarely enters in the same form it arrived from the wall socket. The first thing that usually happens is conversion. Alternating current from the grid is often transformed into direct current. Voltages are reduced, signals are smoothed, noise is filtered out. By the time electricity reaches the sensitive parts of a device, it has been refined into something stable and predictable. This conversion exists because most modern technology depends on consistency. Electronic components are sensitive to fluctuations. Small changes in voltage can cause errors, overheating, or failure. So machines begin by reshaping electricity into a form that can be trusted. Power supplies perform this work quietly. They contain transformers, rectifiers, capacitors, and regulators. Each plays a role in turning a rough, oscillating input into a calm, steady output. This process does not add intelligence, it adds reliability. It ensures that everything downstream behaves as expected. Once electricity is stabilized, it can be used to do three main kinds of work inside machines. It can move things, it can sense things, and it can process information. Often, all three happen at once. Motion is the most familiar. Electric motors convert electrical energy back into mechanical motion. This happens everywhere, from fans and pumps to hard drives and industrial machinery. Inside a motor, electricity interacts with magnetic fields to produce force. Coils energize, magnetic conditions shift. Parts are pulled and pushed in coordinated ways. Rotation emerges. What makes electric motors so powerful is control. The speed, direction, and torque of a motor can be adjusted by changing how electricity is supplied. Increase voltage, and the motor speeds up. Change the timing of currents, and direction reverses. Modify the pattern, and motion becomes smoother or stronger. This level of control allows machines to respond dynamically. A washing machine adjusts spin cycles, a drill responds to pressure, a vehicle modulates acceleration. Electricity makes motion adaptable rather than fixed. Sensing is less obvious, but just as important. Many machines rely on sensors that convert physical conditions into electrical signals. Temperature sensors change resistance. Light sensors generate current when photons strike them. Pressure sensors deform slightly, altering electrical behavior. Motion sensors detect changes in fields. In all these cases, electricity acts as a translator. It turns physical change into something that can be measured and compared. A sensor does not decide what the change means. It simply produces a signal that reflects it. The interpretation comes later. That interpretation happens in the third category, information processing. This is where electricity becomes abstract. Inside electronic circuits, electricity no longer represents energy alone. It represents states, on or off, high or low, yes or no. These states are implemented using tiny structures that allow or block the movement of electrons under specific conditions. Transistors are the most important of these structures. A transistor is not a switch you flip by hand. It is a region of material that responds to small electrical signals by allowing large ones to pass or stop. By arranging transistors in large numbers, machines can perform logical operations. They can compare signals, store values, and execute sequences of actions. All of this happens because electricity is predictable. When conditions are set, electrons respond reliably. This predictability is what allows machines to behave consistently. A computer does not remember because it wants to. It remembers because electrical states are maintained in physical structures. When power is present, those structures hold charge or maintain conditions. When power is removed, those conditions collapse. Unless they are deliberately preserved in a different form, inside modern devices, electricity moves through layers of organization. At the lowest level, electrons respond to fields. At the next level, components shape that movement. At higher levels, patterns of movement represent instructions, images, sounds, and decisions. This layering is what makes modern technology feel complex, even though its foundation is simple. The same electricity that heats a wire also carries a video signal. The difference lies entirely in how the movement is structured. Timing plays a crucial role here. Many machines rely on precise electrical rhythms. Clocks inside devices generate regular pulses. These pulses coordinate actions. They tell circuits when to read signals, when to change states, when to move data. Without timing, electricity would still flow, but it would not be meaningful. Random motion does not produce computation. Ordered motion does. The order comes from carefully designed pathways and constraints. This is why modern machines are full of components that do not obviously consume energy in dramatic ways. Tiny currents move through microscopic structures. Heat is generated, but in small amounts spread across large areas. The work being done is logical rather than mechanical. Electricity inside machines also enables feedback. A system can measure its own output and adjust accordingly. A thermostat senses temperature and adjusts heating. A processor monitors its workload and changes speed. A motor controller detects resistance and compensates. Feedback depends on electricity's ability to move quickly and reliably. Signals must travel faster than changes occur. This speed allows machines to react before conditions become unstable. Communication between machines is another extension of this idea. Electrical signals carry information along wires, through cables, and across circuits. Even when wireless transmission is involved, electricity remains central. Radio waves are generated by oscillating electric charges. Receivers convert those oscillations back into electrical signals. Inside devices, communication happens constantly. Different parts exchange signals. Data moves from memory to processor. Commands move from software to hardware. Electricity is the medium that makes this internal conversation possible. What makes this possible at scale is miniaturization. As components became smaller, electrical paths became shorter. Signals could travel faster. Less energy was needed to switch states. Heat became easier to manage. Modern technology depends on controlling electricity at extremely small scales. Features measured in billionths of a meter guide electrons with astonishing precision. At that scale, quantum effects become significant, but they are harnessed rather than avoided. Despite this complexity, the underlying behavior remains the same. Charge responds to fields. Movement follows paths. Constraints shape outcomes. Nothing fundamentally new has been added. The novelty lies in arrangement. This arrangement allows electricity to represent ideas. Numbers, images, text, sound, and instructions all become patterns of electrical states. Machines do not understand these patterns. They manipulate them according to rules. This distinction matters. Electricity enables modern technology, but it does not explain it fully. Human decisions determine what patterns mean. Engineers design systems that interpret electrical behavior in useful ways. Power management becomes critical as machines grow more capable. Sensitive electronics require stable conditions. Surges and noise can disrupt operation. This is why devices include layers of protection, filtering, and isolation. Electricity inside machines is rarely raw. It is conditioned, monitored, and controlled continuously. This conditioning makes devices robust, but it also makes them dependent on electricity behaving within expected limits. Failures often occur when those limits are exceeded. Overvoltage damages components, undervoltage causes instability, heat buildup degrades materials. These failures remind us that electricity is still a physical process, not an abstract service. Modern technology also reveals electricity's role in efficiency. Machines are designed to do more with less electrical energy. Processing that once required entire rooms now happens on chips smaller than a fingernail. This efficiency comes from reducing unnecessary motion and focusing electricity where it matters. Sleep modes, low power states, and adaptive performance are all ways of managing electrical behavior. Devices do not need full power all the time. They adjust dynamically. This adaptability echoes the behavior of the grid, but at a smaller scale. Inside machines, electricity is constantly being balanced against demand, just as it is across regions. One of the most striking aspects of electricity inside modern technology is how little of it is devoted to visible output. Screens emit light, speakers produce sound, motors move parts. But much of the electrical activity supports internal coordination. Processors consume energy to move information, not objects. Memory uses energy to maintain states. Communication interfaces consume energy to translate between systems. This invisible work defines modern machines. Electricity also enables abstraction. Software exists because hardware can be reconfigured electrically. A machine can perform different tasks without being physically altered. Changing patterns of electrical behavior changes function. This flexibility is unprecedented in earlier technologies. Mechanical systems had fixed purposes. Electrical systems can be repurposed endlessly within their physical limits. Despite this, the fundamentals remain grounded. If electricity stops, machines stop. If power becomes unstable, behavior degrades. Electricity is the enabler, not the origin of intelligence or intention. Understanding electricity inside machines demystifies modern technology. It reveals that complexity arises from layers of simple interactions carefully organized. There is no hidden consciousness in circuits. There is coordination. This perspective also highlights continuity with earlier stages of the story. The same principles that govern static sparks and flowing currents govern microprocessors and sensors. The scale has changed. The precision has increased. The behavior has not. Electricity inside machines is where energy, motion, and information converge. It is where invisible movement becomes visible behavior. It is where physical law meets human design. And as deeply embedded as electricity is in machines, its influence does not stop there. It also operates inside living systems, shaping sensation, movement, and thought, using many of the same principles, but arranged in ways that evolved rather than being engineered, pointing toward an even more intimate relationship between electricity and life itself. Electricity does not enter the human story only through wires, machines, and outlets. Long before humans learned how to generate or control electrical currents externally, electricity was already at work inside living bodies, not as sparks or shocks, but as quiet, precise signals that make sensation possible, coordinate movement, and keep vital systems running without conscious effort. The electricity inside the human body is not an add-on to biology. It is woven into its most basic functions. At first glance, the human body does not look electrical. It is warm, wet, and organic, not metallic or mechanical. But those qualities are exactly what make biological electricity possible. Living tissue is full of charged particles dissolved in fluid. Ions move freely in water-based environments. This mobility allows electrical effects to occur without wires, using membranes, gradients, and chemical structure instead. The foundation of biological electricity is the same as all electricity: charge imbalance and controlled movement. Cells maintain differences in electrical charge between their interior and exterior. This difference is not accidental. It is carefully created and constantly maintained using energy. Every cell in the body is surrounded by a membrane. This membrane is thin, flexible, and selectively permeable. It allows some particles to pass while blocking others. Among the particles it regulates are ions such as sodium, potassium, calcium, and chloride. Each carries an electric charge. By actively moving ions in and out, cells establish an electrical difference across the membrane. The inside of the cell is usually more negatively charged than the outside. This difference is known as a membrane potential. It represents stored electrical energy, similar in concept to a charged battery, though much smaller in scale. Maintaining this imbalance requires work. Cells use energy from metabolism to power molecular pumps embedded in their membranes. These pumps move ions against their natural tendencies, creating and preserving electrical gradients. If the pumps stop, the gradients collapse, and the electrical properties of the cell disappear. This constant maintenance highlights an important point. Biological electricity is not passive, it is actively sustained. Life expends energy to remain electrically organized. The purpose of this organization becomes clear in specialized cells, especially neurons and muscle cells. Neurons use electrical signals to transmit information rapidly over long distances within the body. Muscle cells use electrical changes to trigger contraction. In neurons, electrical signaling begins when the membrane potential changes. Under resting conditions, the neuron maintains a stable imbalance. But when stimulated, specific channels in the membrane open. Ions rush in or out, driven by both concentration differences and electrical attraction. This movement causes a rapid change in membrane potential. The inside of the cell becomes less negative, and in some cases briefly positive. This change is not gradual. It happens quickly and follows a predictable pattern. This event is called an action potential. An action potential is not electricity flowing down a wire. It is a wave of electrical change that travels along the membrane of the neuron. Each segment of membrane triggers the next, creating a chain reaction. The signal moves quickly, even though individual ions move only short distances. This mechanism allows information to travel far faster than chemical diffusion alone could manage. Sensory input, motor commands, and internal coordination all depend on this speed. Once an action potential reaches the end of a neuron, it does not usually jump directly to the next cell as electricity. Instead, the electrical signal triggers the release of chemical messengers called neurotransmitters. These chemicals cross the small gap between cells and bind to receptors on the next neuron. Those receptors then cause electrical changes in the receiving cell, restarting the process. Electricity and chemistry work together, each handling what it does best. Electricity provides speed. Chemistry provides flexibility and modulation. Muscle cells use a similar principle. Electrical signals alter membrane potentials, leading to the release of calcium ions inside the cell. Calcium triggers interactions between proteins that cause the muscle to contract. The electrical signal itself does not do the physical work. It coordinates the conditions that allow work to happen. The heart provides a particularly clear example of biological electricity at work. Heart muscle cells are electrically coupled. They coordinate their contractions through waves of electrical activity that propagate in a precise sequence. This coordination ensures that the heart beats rhythmically and efficiently. The electrical activity of the heart is strong enough to be measured at the surface of the body. Instruments detect these signals and represent them as patterns. These patterns reflect the timing and health of the heart's electrical system. Importantly, the heart does not require conscious control to maintain this activity. Specialized cells generate regular electrical impulses automatically. The rest of the heart responds in sequence. This autonomy shows how deeply electrical behavior is embedded in biological systems. Electricity inside the body is also essential for sensation. Touch, vision, hearing, taste, and smell all rely on electrical signals generated in response to physical or chemical stimuli. Light striking the retina causes electrical changes in cells. Sound waves cause mechanical movement that is translated into electrical signals. Pressure, temperature, and chemical composition all influence ion channels and membrane potentials. In each case, electricity serves as the common language. Diverse stimuli are converted into a form that the nervous system can process and compare. This standardization allows the brain to integrate information from many sources. The brain itself is an electrical organ, though not in the way it is sometimes imagined. It does not store thoughts as electrical charges or generate ideas through sparks. Instead, it coordinates vast networks of neurons whose electrical states change in complex patterns. At any given moment, billions of neurons are maintaining membrane potentials, firing action potentials, releasing neurotransmitters, and responding to signals. This activity is structured, but not rigid. Patterns shift constantly as the brain responds to internal and external conditions, The electrical activity of the brain can be measured in aggregate. These measurements reveal rhythms associated with different states such as sleep, attention, or rest. These rhythms are not imposed from outside, they emerge from interactions between neurons. Despite this electrical complexity, the brain's activity is slow compared to electronic circuits. Action potentials take milliseconds, not nanoseconds. This difference highlights that biological electricity is optimized for adaptability and integration rather than raw speed. Another important distinction is that biological electrical systems operate in a wet, variable environment. Temperature, chemical composition, and metabolic state all influence electrical behavior. Cells adapt continuously. This adaptability allows life to function across a wide range of conditions. Electricity in the body is also inherently local. Signals travel along specific pathways. They are not broadcast indiscriminately. This localization prevents interference and allows parallel processing. Different parts of the nervous system can operate simultaneously without confusion. The body also includes protective mechanisms to prevent uncontrolled electrical activity. Ion channels open and close in regulated ways. Refractory periods prevent signals from traveling backward or firing too frequently. These constraints ensure stability. When these systems fail, the consequences can be severe. Disrupted electrical signaling can lead to loss of sensation, paralysis, irregular heart rhythms, or seizures. These conditions illustrate that biological electricity is not optional. It is essential. At the same time, the body is resilient. Electrical systems can adapt to damage. New pathways can form. Sensitivity can change. This plasticity reflects the living nature of biological electricity. Comparing biological electricity to technological electricity reveals both similarities and differences. Both rely on charge, movement, and gradients. Both require structure and control, but biological systems use soft materials, chemical support, and self-repair. Technology uses rigid materials and external control. Biology integrates electricity into metabolism and growth. One is engineered, the other evolved. Understanding electricity inside the body also reshapes how external electricity is viewed. Electrical medical devices interact with the body's own electrical systems. Pacemakers provide rhythm. Nerve stimulators modulate signals. Electrodes measure activity. These interactions work because they speak the same language. External electrical signals can influence internal ones, but only within limits defined by biology. The presence of electricity inside the body reminds us that electricity is not foreign to life. It is not an artificial imposition. It is a natural behavior that living systems have learned to use. This realization brings the story of electricity full circle. The same principles that govern lightning, generators, and power grids also govern sensation, movement, and thought. The scale and context differ, but the behavior is continuous. Electricity inside the human body is not dramatic. It does not crackle or glow. It works quietly, reliably, moment by moment, maintaining coordination and responsiveness. Its success lies in its subtlety. As electricity became a tool outside the body, it mirrored functions that life had already mastered: signaling, control, timing, coordination. The difference is not in the physics, but in the organization. Recognizing this continuity helps dissolve the boundary between natural and technological electricity. It shows that modern systems are extensions of principles that have been at work inside living beings all along. And just as electricity inside the body must be regulated, measured, and protected, so too must electricity outside it. Understanding how electricity behaves in living systems sharpens awareness of its risks, limits, and responsibilities, setting the stage for thinking carefully about control, measurement, and safety wherever electricity flows. Electricity is invisible, and that invisibility creates a problem. If you cannot see something directly, you cannot rely on instinct alone to judge its presence, strength, or behavior. Early encounters with electricity made this clear very quickly. Sparks and shocks were obvious, but they were also unreliable indicators. They arrived suddenly, disappeared just as quickly, and revealed very little about what was happening in between. For electricity to become dependable, it had to become measurable. For it to become safe, it had to be controllable. And for it to become part of everyday life, it had to earn trust. Measurement was the first step toward all three. Measuring electricity did not mean seeing electrons or fields directly. It meant finding consistent ways to relate electrical behavior to observable effects. How much charge was moving, how strong the push was, how much energy was being transferred. These questions could not be answered by sensation alone. Early electrical measurement relied on comparison rather than absolute values. Objects deflected, needles moved, wires heated. These effects were used as stand-ins for invisible quantities. If one setup produced more deflection or more heat than another, it was assumed to involve more electrical activity. This approach was crude, but it established a critical principle. Electricity could be compared, not just experienced. As electrical systems became more complex, comparison was no longer enough. Engineers needed to know not just that one current was stronger than another, but by how much. Devices needed to be designed with predictable behavior. Safety margins depended on knowing limits. This led to the development of standardized quantities. Electrical pressure, rate of charge movement, and opposition to flow were given formal definitions. These quantities did not create electricity. They described it. They provided a language for talking about invisible behavior with precision. Measurement devices evolved alongside these definitions. Instruments were built to respond in calibrated ways to electrical conditions. A measured deflection corresponded to a known value. Over time, these instruments became more accurate, more stable, and more portable. The existence of reliable measurement changed how electricity was perceived. It became less mysterious and more accountable. If something went wrong, it could be diagnosed. If performance varied, it could be corrected. Measurement turned electricity from a spectacle into a system. Control followed naturally. Once electrical behavior could be measured, it could be managed. Control does not mean domination. It means shaping conditions so that outcomes remain within desired bounds. The simplest form of control is interruption. A switch opens or closes a path. When the path is open, current stops. When it is closed, current flows. This binary control is deceptively powerful. It allows electricity to be present without being active, ready without being dangerous. Beyond simple interruption, control involves regulation. Electrical systems must maintain stable conditions despite changing demands. Voltage regulators smooth out fluctuations. Current limiters prevent excessive flow. Protective devices disconnect systems when thresholds are exceeded. These controls exist because electricity responds immediately to conditions. It does not wait for permission. If a path exists, charge moves. If resistance drops, current increases. Control devices ensure that these responses do not lead to damage. One of the most important control mechanisms is feedback. Feedback involves measuring output and using that information to adjust input. This principle appears everywhere in electrical systems. Power supplies monitor voltage and adjust internally. Motors sense speed and correct deviations. Grids monitor frequency and redistribute load. Feedback works because electricity moves quickly. Measurements and adjustments can happen faster than many disturbances develop. This speed allows systems to stabilize themselves continuously. Another crucial aspect of control is isolation. Electrical systems are divided into sections so that problems remain local. Fuses and circuit breakers sacrifice continuity to preserve safety. They interrupt flow when conditions become dangerous. This interruption is not a failure. It is a designed response. It reflects an understanding that electricity cannot be reasoned with once it is moving. It must be constrained in advance. Control also involves shaping electricity rather than simply stopping it. Resistors slow it down. Capacitors store and release it. Inductors resist changes in its motion. These components do not eliminate electricity, they influence how it behaves over time. By combining these elements, engineers create circuits that respond predictably. A device turns on smoothly rather than abruptly. Signals are filtered to remove noise. Power is delivered steadily even when demand fluctuates. All of this depends on trusting that electricity will behave according to established rules. That trust is not blind. It is earned through consistency. Electrical laws do not change based on location or intention. They hold as long as conditions are met. This reliability allows systems to be layered. Simple components combine to form complex behavior. Designers do not need to account for every electron individually. They rely on statistical regularity. Trust also comes from redundancy. Critical systems are backed up. Multiple pathways exist. If one component fails, another takes over. This redundancy acknowledges that while electrical behavior is predictable, physical components are not infallible. The grid embodies this principle. Multiple generators, multiple lines, and multiple control centers work together. No single failure should bring everything down. This design reflects an understanding of both electrical certainty and material uncertainty. Trust in electricity also depends on clear boundaries between users and systems. People interact with electricity through interfaces designed to limit exposure. Outlets, plugs, insulation, and enclosures exist to make electricity accessible without being intimate. These interfaces work because electricity follows paths. If paths are controlled, behavior is controlled. This path-based nature makes electricity easier to manage than many other forms of energy. However, trust does not mean complacency. Electrical systems require maintenance. Insulation degrades, connections loosen, components age. Without attention, predictable behavior gives way to failure. This need for maintenance reinforces the idea that electricity is a partnership between physical law and human oversight. The laws provide consistency. Humans provide care. Measurement plays a role here as well. Monitoring systems detect changes before they become problems. Heat sensors, current monitors, and diagnostic signals all provide early warning. This allows intervention without waiting for visible failure. Trust also has a cultural dimension. People rely on electricity without thinking about it because it has proven dependable over time. This reliance shapes behavior and expectations. When electricity is absent, the disruption feels disproportionate to the physical change. This reaction reveals how deeply electricity has been integrated into modern life. It is not just energy, it is coordination. It synchronizes activity across distances and schedules. Because electricity is invisible, trust often goes unnoticed until it is broken. Flickering lights, unexpected shutdowns or shocks remind us that electricity is not passive. It demands respect. At the same time, excessive fear can be paralyzing. Understanding how electricity behaves reduces fear without eliminating caution. Knowledge replaces superstition with awareness. This balance between trust and respect is essential. Electricity is neither benevolent nor malicious. It responds to conditions. When conditions are right, it serves reliably. When conditions are wrong, it exposes consequences. The act of measurement bridges this gap. It turns invisible behavior into numbers and signals that can be understood. Control uses that understanding to guide outcomes. Trust emerges when systems behave as expected over time. This progression mirrors the broader story of electricity, from unpredictable sparks to steady currents, from curiosity to infrastructure, from spectacle to background presence. As electrical systems continue to evolve, measurement and control become even more important. New technologies push limits. Higher densities, faster signals, and more sensitive components leave less room for error. The same principles apply. Measure accurately, control carefully, design with failure in mind. Trust emerges from consistency, not assumption. Electricity will always remain invisible. That will not change. But invisibility does not imply unknowability. Through measurement and control, invisible power becomes legible and manageable. This legibility allows electricity to fade into the background of daily life, not because it is unimportant, but because it is understood well enough to be trusted. And yet, even with trust and control, electricity retains an edge. It can still surprise when assumptions fail. It can still demand attention when boundaries are crossed. That tension is part of what makes the electricity enduringly relevant. It is familiar but not trivial, reliable but not forgiving. Understanding how to measure and control electricity prepares us for the moments when it behaves unexpectedly, and it frames the importance of safety, limits, and responsibility, especially when invisible power is woven so deeply into environments designed for human use. Electricity works best when it is boring. When lights turn on without hesitation, machines hum steadily, and systems respond exactly as expected, electricity fades into the background. But when something goes wrong, it demands attention immediately. Failure reveals aspects of electricity that normal operation hides. Risk becomes visible. Safety stops being an abstract concept and becomes a practical necessity. Understanding what happens when electricity goes wrong is not about fear. It is about recognizing that electricity always follows physical rules, even when human expectations fail. Electrical failure does not usually begin dramatically. It often starts with small deviations. A connection loosens slightly. Insulation degrades over time. Heat builds up in places where it should not. These changes are gradual and easy to miss because electrical systems are designed to tolerate a certain amount of imperfection. They are built with margins, but those margins are not infinite. One of the most common ways electricity goes wrong is through unintended paths. Electricity does not care whether a path is desirable. It responds only to availability and resistance. If a conductive path appears where none was intended, electricity will use it. This can happen when insulation breaks down, when moisture creates a bridge, or when damaged components expose conductive material. Unintended paths can redirect current in ways that cause damage or danger. Heat builds up where components were not designed to handle it. Materials degrade faster. In extreme cases, fires start. These outcomes are not acts of malice. They're consequences of electricity doing exactly what it always does. Heat is one of the clearest signs of electrical trouble. Resistance converts electrical energy into heat. Under normal conditions, this heat is managed. Wires are sized appropriately. Components are rated for expected loads. Ventilation removes excess warmth. When something changes, heat accumulates. Overloaded circuits are a common example. If too much current flows through a wire, the wire heats up. If the heat cannot dissipate, insulation softens or melts. This exposes conductors, creating new unintended paths. The problem compounds. What began as a minor overload can escalate quickly. This is why electrical systems are designed with protective devices that respond faster than damage develops. Fuses and circuit breakers are not inconveniences. They are deliberate points of failure. They sacrifice continuity to preserve safety. When a fuse blows or a breaker trips, it interrupts the flow of electricity. This interruption prevents heat from continuing to build. It isolates the problem. It forces attention. Without this intervention, electricity would continue flowing until something else failed, often in a more destructive way. Short circuits represent another class of failure. A short circuit occurs when electricity finds a path with very low resistance that bypasses intended loads. This causes current to increase dramatically. The increase happens faster than most components can tolerate. Short circuits often result from physical damage. A wire is cut, insulation is pierced, conductors touch. The resulting surge can be violent. Sparks fly. Components fail instantly. Protective devices are designed to respond to this sudden change, but even brief surges can cause damage. What makes short circuits dangerous is not just the energy involved, but the speed. Electrical systems react quickly. Damage can occur in fractions of a second. This is why prevention is so important. Once a short circuit develops, the window for intervention is very small. Another failure mode involves grounding. Grounding provides a reference point for electrical systems and a safe path for unintended currents. When grounding is inadequate or absent, stray electrical energy has nowhere safe to go. It may travel through structures, equipment, or people. Electric shock is one of the most direct risks associated with electrical failure. A shock occurs when electrical current passes through the body. The severity depends on many factors: the amount of current, the path it takes, the duration, the condition of the skin, the surrounding environment. The human body conducts electricity because it contains water and ions. This does not mean the body is a good conductor, but it is conductive enough to be affected. Electrical current passing through the body can interfere with nerve signals, muscle control, and heart rhythm. Low-level shocks may be startling or painful but not dangerous. Higher currents can cause muscle contractions that prevent release from the source. Very high currents can disrupt vital functions or cause burns. One of the most dangerous aspects of electrical shock is unpredictability. The same voltage can produce different effects under different conditions. Wet skin reduces resistance. Metal surfaces provide better contact. These variables make it difficult to rely on intuition alone. This unpredictability reinforces the need for design-based safety rather than behavior-based assumptions. Systems are built to minimize exposure. Insulation, enclosures, and grounding exist to keep electricity where it belongs. Fire is another major risk when electricity goes wrong. Electrical fires are particularly dangerous because they may start in hidden places, inside walls, behind panels, under floors. By the time they're noticed, they may already be advanced. Electrical fires often result from sustained overheating rather than sudden sparks. Loose connections create localized resistance. That resistance generates heat. Over time, nearby materials ignite. Because the process is slow, it can evade detection. This is why electrical codes emphasize proper connections, appropriate materials, and regular inspection. Safety is not achieved by avoiding electricity. It is achieved by respecting how electricity behaves. Large-scale electrical failures introduce additional risks. Power outages disrupt critical systems. Hospitals rely on backup power. Transportation systems depend on signaling. Communication networks require continuous operation. When large sections of the grid fail, the immediate absence of electricity can be as dangerous as its uncontrolled presence. Traffic lights go dark. Heating and cooling systems stop. Water pumps fail. Modern life assumes electrical continuity. This dual risk, danger from both excess and absence, makes electricity unique. It must be present, but controlled. Reliable, but constrained. Failures at grid scale often result from cascading effects. One component fails, load shifts to others. Those components become stressed. Additional failures occur. This chain reaction can spread quickly if not contained. Grid design accounts for this by segmenting systems and adding redundancy. Automatic protection isolates faults. Operators reroute power. These measures limit the scope of failure. Despite this, large outages still occur. Severe weather, equipment failure, and human error can overwhelm safeguards. These events highlight the complexity of coordinating electricity across vast networks. Safety in electrical systems is not achieved by eliminating risk entirely. It is achieved by managing risk intelligently. This involves anticipating failure modes, designing responses, and accepting that some failures are inevitable. Human interaction with electricity introduces another layer of risk. People modify systems, they add devices, they use equipment in unintended ways. These actions can create conditions designers did not anticipate. This is why safety standards evolve. As usage patterns change, guidelines are updated. What was safe in one era may not be safe in another. Electrical systems must adapt to new demands. Education also plays a role. Understanding basic electrical principles reduces risky behavior. Knowing that water increases conductivity changes how people approach electrical devices. Knowing that damaged cords are dangerous encourages replacement. However, safety cannot rely solely on knowledge. Systems must be designed to protect even when knowledge fails. Children, for example, do not understand electrical risk. Safety features must account for that. This philosophy is reflected in protective design. Outlets are recessed. Plugs are shaped to reduce contact. Devices shut down automatically under fault conditions. These features assume imperfect behavior and compensate for it. One of the challenges of electrical safety is complacency. Because electricity usually behaves reliably, people forget that it is still energy in motion. Familiarity dulls caution. This is not a moral failing, it is a human tendency. Safety systems exist to counter that tendency. They provide protection even when attention lapses. They are not signs of mistrust, they are acknowledgements of reality. Electrical failure also reveals the interconnectedness of systems. A fault in one place can have effects elsewhere. This interconnectedness magnifies both benefit and risk. Electricity's ability to coordinate systems makes it powerful. It also makes it vulnerable. This vulnerability is why maintenance matters. Inspections, testing, and upgrades are not optional extras. They are part of keeping electricity within safe bounds. Aging infrastructure presents particular challenges. Materials degrade, designs become outdated, load patterns change. Systems that were safe under earlier conditions may no longer be adequate. Addressing these challenges requires investment and foresight. It requires acknowledging that electrical safety is not a one-time achievement. It is an ongoing process. At the same time, it is important not to view electricity as inherently dangerous. Risk arises from conditions, not from electricity itself. When systems are designed, maintained, and used appropriately, electricity is remarkably safe. The very fact that electricity is so widely used is evidence of this. Billions of interactions occur every day without incident. That level of reliability is not accidental. It is the result of layered safety measures informed by experience. Failures, when they occur, provide information. They reveal weak points. They drive improvements. Electrical safety standards are written in response to past incidents. Each rule reflects a lesson learned. This learning process continues. New technologies introduce new failure modes, higher power densities, faster electronics, and decentralized generation create new challenges. Safety evolves alongside capability. Understanding what happens when electricity goes wrong also deepens respect for what happens when it goes right. Normal operation represents a balance achieved moment by moment. That balance is easy to overlook. By examining failure, risk, and safety, electricity becomes less abstract and more concrete. It is not a background convenience, it is a managed force. This understanding encourages thoughtful use rather than fear. It frames safety as cooperation with physical law rather than resistance to it. Electricity does not punish mistakes, it reveals them. When conditions allow uncontrolled flow, consequences follow. When conditions are constrained, electricity behaves predictably. Recognizing this helps shift responsibility from electricity itself to system design and use. It is not about avoiding electricity, it is about working with it honestly. As electrical systems become more complex and more deeply embedded in daily life, the margin for error narrows in some areas and widens in others. Automation reduces some risks. Complexity introduces new ones. The challenge moving forward is not to eliminate electricity's dangers, but to understand them well enough that safety remains part of the system, rather than an afterthought. This understanding sets the stage for thinking about where electricity is headed, how its role might change, and what new responsibilities will emerge as invisible power continues to shape the future. Thinking about the future of electricity means thinking about change without assuming a single direction. Electricity itself will not transform into something else. The same physical rules will continue to apply. Charges will respond to fields, energy will move through circuits. What will change is how electricity is produced, managed, distributed, and integrated into human systems. The future of electricity is not about discovering a new kind of power. It is about rearranging familiar behavior to meet new constraints. One of the strongest pressures shaping that future is scale. Demand for electrical energy continues to grow, not just because populations increase, but because more activities become electrically mediated. Transportation, heating, communication, manufacturing and computation increasingly rely on electricity rather than direct combustion or mechanical energy. This shift concentrates energy needs into electrical systems. At the same time, expectations around reliability and cleanliness are rising. Electricity is increasingly expected to be available continuously, affordably, and with minimal environmental impact. These expectations create tension because electricity itself does not exist in isolation. It reflects how energy is generated and managed upstream. A major theme in the future of electricity is diversification of sources. For much of the electrical age, large centralized power plants dominated. They relied on concentrated energy sources and produced electricity at scale. That model is changing. New generation methods are distributed, variable, and geographically dependent. Wind and solar energy are central examples. They convert naturally occurring flows into electrical power, without consuming fuel in the traditional sense. This reduces emissions and resource depletion, but it introduces variability. The sun does not always shine. The wind does not always blow. Electricity production becomes less predictable. This unpredictability challenges traditional grid design. Power systems were built around controllable generation. Operators could increase or decrease output based on demand. Variable sources reverse that relationship. Supply fluctuates independently of demand. The response to this challenge is not singular. It involves better forecasting, more flexible grids, and improved storage. Forecasting reduces uncertainty by anticipating patterns. Flexibility allows systems to adapt quickly. Storage bridges the gap between production and use. Energy storage is one of the most active areas of development. Batteries, once primarily associated with portable devices, are becoming central to grid-scale planning. Large battery installations store excess electricity when supply exceeds demand and release it when demand rises. This storage does not eliminate variability, but it smooths it. It turns intermittent generation into something closer to continuous supply. Storage also enables new forms of grid behavior, allowing electricity to be shifted in time as well as space. Beyond batteries, other storage methods continue to evolve. Pumped hydro uses excess electricity to move water uphill, storing energy as gravitational potential. Thermal storage captures heat for later conversion. Each method has advantages and limitations tied to geography, efficiency, and scale. The future grid is likely to be more layered than today's. Centralized generation will coexist with distributed sources. Homes, businesses, and communities may generate some of their own electricity while remaining connected to larger networks. This hybrid structure changes the role of users. Consumers become participants. Electricity flows both ways. Small generators feed into the grid. Devices respond to price signals. Usage patterns adapt dynamically. Managing this complexity requires intelligence, but not intelligence in the human sense. It requires automation, sensing, and coordination. Electricity will increasingly be accompanied by information about its own state. Smart grids are an expression of this trend. Sensors throughout the system monitor conditions in real time. Control systems respond automatically. Faults are detected and isolated quickly. Demand is balanced dynamically. These capabilities do not change the physics of electricity. They change how humans interact with it. Decision-making shifts from manual control to algorithmic management. Another area of transformation is transportation. Vehicles are transitioning from internal combustion engines to electric motors. This shift changes not only how energy is used, but when and where it is drawn from the grid. Electric vehicles represent both load and storage. They consume electricity, but they also carry batteries. Coordinating charging times can reduce strain on the grid. In some cases, vehicles may even supply electricity back to the system temporarily. This blurring of roles reinforces the idea that the future of electricity is about coordination rather than raw generation. Electricity becomes part of a feedback loop between users, devices, and infrastructure. At the same time, electrification increases the importance of resilience. As more systems depend on electricity, the consequences of failure grow. Outages affect transportation, communication, and essential services simultaneously. This increases emphasis on redundancy, decentralization, and rapid recovery. Systems are designed to degrade gracefully rather than collapse abruptly. Local generation can sustain critical loads. Microgrids isolate and reconnect as needed. Climate change adds another layer of complexity. Extreme weather affects generation, transmission, and demand. Heat waves increase cooling needs. Storms damage infrastructure. Water availability affects hydroelectric generation. Designing electrical systems for the future requires accounting for these stresses. Infrastructure must be robust under a wider range of conditions. Planning must consider long-term trends rather than historical averages. Another dimension of the future of electricity involves materials and efficiency. As systems become more dense and more capable, losses become more significant. Reducing resistance, improving conversion efficiency, and managing heat remain central goals. Advances in materials science influence these efforts. Better conductors, improved insulation, and more efficient semiconductors allow electricity to be used more effectively. Even small efficiency gains matter at scale. There is also increasing interest in using electricity not just as energy, but as a way to reorganize other systems. Electricity can drive chemical processes, produce fuels, and enable manufacturing pathways that are difficult or impossible with direct combustion. This expands the role of electricity beyond consumption into transformation. Electricity becomes a tool for reshaping how energy flows through society. However, this expansion also raises questions about equity and access. Electrical infrastructure reflects investment decisions. Regions with robust systems benefit more readily from new technologies. Regions without them risk falling further behind. The future of electricity is therefore not purely technical. It is also social and political. Decisions about infrastructure shape opportunity. Pricing structures influence behavior. Regulation balances innovation and stability. Trust remains central. As systems become more complex and automated, transparency matters. People need to trust that electricity will be available, affordable, and safe. That trust depends on both performance and governance. Cybersecurity becomes part of this picture. As electrical systems rely more on digital control, they become vulnerable to new kinds of failure. Protecting infrastructure involves not only physical safeguards, but informational ones. This does not make electricity less reliable by default. It makes reliability dependent on broader considerations. The future grid is as much about information flow as energy flow. At the smallest scales, electricity continues to push boundaries in computation. Processing power increases, energy per operation decreases, devices become more efficient and more integrated into daily life. This efficiency reduces energy demand per task, but overall demand may still rise as tasks multiply. The future of electricity involves balancing these trends. Another important consideration is how electricity is valued. Pricing mechanisms influence consumption. Time-based pricing encourages use when supply is abundant. Incentives shape investment. These mechanisms rely on the ability to measure and communicate electrical conditions accurately. Once again, measurement and control underpin progress. Despite these changes, the future of electricity is not a departure from its past. It is an extension. The same principles apply. Electricity responds to differences. It flows along paths. It transfers energy. What changes is how those paths are arranged. In many ways, the future of electricity is about making invisible coordination more visible to systems, even as it remains invisible to users. Automation hides complexity while managing it. This creates a paradox. Electricity becomes more essential and more complex at the same time that it becomes less noticeable in daily experience. When systems work well, electricity feels effortless. The challenge is ensuring that effortlessness does not obscure responsibility. Energy choices have consequences. Infrastructure decisions have long-term effects. Electricity may be invisible, but its impacts are not. Looking forward, electricity is likely to become even more deeply embedded in human activity. It will shape how energy is produced, how systems interact, and how societies adapt to change. What will not change is the need to understand electricity as behavior rather than substance. It will remain a process, not a thing, a relationship between charge, motion, and constraint. That understanding provides continuity across past, present, and future. It allows new technologies to be understood as rearrangements of familiar principles rather than unexplained novelties. The future of electricity is not about abandoning what we know. It is about applying it more carefully, more broadly, and with greater awareness of consequences. As electricity continues to expand its role, it invites a final kind of reflection, not on how it works or where it comes from, but on how thoroughly it has become part of the background of existence, shaping experience without demanding attention, even as it quietly enables nearly everything that defines modern life. Electricity does not feel like a force we live inside, and yet that is exactly what has happened. It surrounds us, moves through the spaces we occupy, and responds continuously to what we do, all without asking to be noticed. Like a river that has been carefully redirected, reinforced, and hidden behind walls, electricity flows steadily beneath the surface of daily life. We do not see it rushing past, but everything around us is shaped by its movement. What makes this invisible river remarkable is not its power alone, but its consistency. Electricity does not sleep. It does not pause unless something forces it to. Every second, generators turn, grids adjust, and systems balance themselves so that the moment you need energy, it is already there. This coordination happens without awareness on our part. We move through rooms, press buttons, and make plans as if electricity were a permanent feature of the world, like gravity or air. In a sense, it has become that permanent. Not because it is natural in the way sunlight is natural, but because it has been woven so deeply into human systems that removing it would unravel far more than convenience. Electricity now supports memory, communication, comfort, movement, and safety. It underpins schedules, economies, and expectations. It defines what feels normal, and yet electricity itself has not changed. The electrons moving through wires today behave no differently than they did centuries ago. The same forces apply, the same tendencies toward balance remain. What has changed is how carefully those tendencies are guided. What was once a rare and startling phenomenon has become something that is shaped moment by moment to fit human needs. This shaping did not happen all at once. It emerged through observation, trial, error, and refinement. Through sparks that surprised, currents that endured, machines that multiplied capability, and networks that demanded coordination. Each step added structure, not to electricity itself, but to the paths it was allowed to follow. Living inside this invisible river means living inside systems that assume reliability. Lights are expected to turn on, information is expected to travel instantly, devices are expected to respond. When these expectations are met, electricity disappears into the background. When they are not, its absence feels immediate and disruptive. That reaction reveals something important. Electricity is not just energy, it is timing. It is coordination across distance. It is shared agreement between countless systems that all respond to the same underlying rules. When electricity falters, the disruption is not just physical, it is organizational. Despite this dependence, electricity remains indifferent. It does not adapt to our habits or preferences. It does not compensate for misunderstanding. It follows paths, responds to differences, and transfers energy according to conditions. The responsibility for making it safe, useful, and reliable rests entirely with how those conditions are created and maintained. This is why electricity invites both trust and respect. Trust, because it behaves consistently when systems are designed well. Respect, because it does not forgive carelessness. Neither attitude is sufficient alone. Together they allow electricity to remain what it is most of the time, unnoticed. The quiet success of electricity is that it has become ordinary without becoming trivial. It enables complexity without demanding attention. It allows modern life to function at speeds and scales that would otherwise be impossible, all while remaining largely unseen. Even now, as technologies evolve and systems grow more interconnected, the fundamental relationship remains unchanged. Electricity responds to structure. It flows where paths exist. It transfers energy according to difference and resistance. Everything else, from global networks to personal devices, is built on top of that behavior. Understanding this does not require memorizing formulas or mastering technical language. It requires recognizing that electricity is not the thing we possess, but a process we participate in. Every time we use it, we rely on arrangements that hold imbalance in place just long enough to be useful, then release it safely. Living inside an invisible river also means accepting that we are part of its flow. Our choices affect demand. Our designs shape distribution. Our maintenance determines reliability. Electricity may be invisible, but the systems that guide it are human creations, reflecting priorities, trade-offs, and values. As the world continues to change, electricity will remain central, not because it is new, but because it is adaptable. It does not dictate outcomes, it enables them. It carries energy, information, and coordination wherever paths are prepared. And so, when the lights are low, the room is quiet, and everything is working as it should. Electricity is still there, moving steadily, invisibly, doing exactly what it has always done, seeking balance, following structure, making motion possible, not demanding attention, just flowing on.